Okay. Okay, folks. I'll let you go ahead and get your coffee and take a stretch or whatever, but we'll go ahead and get started with the next panel. This is the part of the proceedings where we get into Astrobiodefense. The title of this next panel is NASA and Planetary Protection. And this is all about astrobiodefense, which is sort of biothreat and biodefense meets space travel. Whenever being a kid of the 1960s, which I am, every time I think about space, I think back to the Apollo launches of the 60s and watching all those astronauts splash down that July 1968, I guess it was 68, watching the moon landing. 69. 69, sorry. Watching the moon landing.
Black and white TV.
Oh, absolutely. Black and white TV with the rabbit ears in a motel in West Virginia. I still remember that night. Anyway, but every time I remember watching that, I remember watching the poor guys, and I guess they were all guys then, get stuck in quarantine. Here they come back from space. They've finally survived. They actually splash down. They're alive. They're back. And then they get stuck in a tin can for like 2 or 3 weeks. I always thought that was particularly cruel. And of course, the explanation was the desire to protect them and us against whatever mysterious microbes or diseases they might have brought back with them. That was a very real concern, born both of the knowledge that such microbes could be coming back with them, and also just the lack of knowledge about what's out there and what they could be exporting or importing into the world. But now, with the expansion of space travel, not only by nation state actors, but also by the private sector, the expansion in terms of frequency, in terms of areas of space that we're traveling to, in terms of the ability to bring elements of space back into the world, there's much more crossover between our world and outer space. And so that threat is even greater than it was back when I was watching the splashdowns in the 1960s. And the threat is not only just the threat of what we'll bring here through our space travel, but also our space exploration and space travel, but also what we might export out to the rest of space. And, whether we'd be exporting the certain microbes that we have, the diseases that we bring with us when we go out into space, that might have the same impact that they're having here, but also that we might be taking microbes and diseases out there which flourish out in those conditions in a way that's even more serious and more severe than they flourish here in the world. And dealing with that bidirectional threat requires quite a bit of thinking and quite a bit of organizational work. And Donna and Susan, two of our commissioners, have written about this. But just when you think about the range of government and private sector activities that need to be oriented toward that bidirectional threat, there's obviously research that needs to be done. There is development of countermeasures to deal with any such diseases. And then the enhancement and adaptation of biosurveillance to address that threat both directions. In addition to the threat, though, there are also opportunities presented by the fact that we're spending more time out in space. Obviously, the conditions, zero gravity and others in space provide opportunity for research and development. And then also just the fact that NASA and others are developing technology to deal with and anticipate this threat means that technologies are being enhanced that can then be applied here in our world in a way to help enhance our biosecurity. So, as I'll say that as I watched that moon landing back in 1969, I never anticipated that we'd be sitting here talking about this threat and the various technologies that might be implicated or might be useful in dealing about this threat. But here we are, and it is a very exciting world to discuss. And we have two of the world's experts here to discuss this with us. And I'm just briefly going to introduce them, and I hope that you take a minute to explain your backgrounds. We have Dr. J.D. Polk, who is the Chief Health and Medical Officer at NASA, and he previously worked at Department of Homeland Security in the then known as the Office of Health Affairs. And then Nick Bernardini is the Planetary Protection Officer within NASA, within the Office of Planetary Protection. And I just, before you leave today, I want your business card because that is the absolute coolest title in the world. Planetary Protection Officer. Sounds like something out of Marvel Comics, as a superhero or something. But I was thinking about it as I read your bio. I thought, that's tough. I have a bad day as a lawyer. I mess up my timesheets or something. You have a bad day and you wipe out extraterrestrial populations. So big responsibilities and a fascinating job. So let me turn it to each of you. I'd love to hear from each of you. I think, Dr. Polk, are you going first?
That's fine. Yeah.
Up to you. Okay. Turn to you first, and then we'll go through both of you, and then we'll have questions. Right?
Thanks.
Thank you.
First, I have to address Secretary Shalala's remark about wanting to be a space medicine doctor. Secretary, it's never too late. We could work something out. Thank you, honorable members of the committee. Thank you for the opportunity to address this vital issue as we prepare for humanity's next great leap, which is the return to the moon and the human-rated missions to Mars, and ensuring the safety and success of these missions while maintaining the integrity of both Earth and the extraterrestrial environments is of paramount importance. One critical area that my office collaborates with the Planetary Protection Officer on is backward planetary protection. The prevention of extraterrestrial contamination of Earth upon the return of astronauts and materials from Mars or other bodies. And unlike uncrewed missions, human-rated missions present a unique challenge, particularly due to the complex microbial ecosystems that exist within the human body itself and then the spacecraft environment. Astronauts and spacecraft inevitably carry bacteria, viruses, and fungi as part of their natural microbiome. And while these microorganisms are typically benign or even beneficial under normal circumstances, the extreme conditions of interplanetary travel could induce DNA mutations or other changes that may potentially alter their behavior. Such changes may result in microorganisms with enhanced virulence, microbial resistance, or entirely novel characteristics. The implications are twofold. First, the risk of affecting astronaut health during the mission, which of course is my paramount important task to prevent. And then two, the potential for inducing these altered microorganisms back to Earth's biosphere upon return. NASA recognizes these concerns and actively leverages both our research and operational knowledge to inform risk-based practices to try to prevent these from occurring. And based on this evidence, NASA is planning on the following mitigations. The first one that we do is comprehensive pre-mission screening. It's important to sample the astronauts' microbiome in order to have a benchmark for comparison when they come back. So we conduct rigorous health screenings and genomic analyses of the astronauts and their habitats and those microbiomes to establish that baseline data. This data can be used to monitor and manage microbial changes during the mission or post-flight. In-mission monitoring and treatment, inclusion of diagnostics and medical treatments to include antibiotics, antivirals, et cetera, to treat an astronaut who had become ill during a return from a deep space planetary mission, and the ability for quarantine and biocontainment if required upon recovery. This will allow for early detection of potential harmful changes in immediate countermeasures. Robust filtration systems will also be used on both spacecraft and any habitat environment that we are engaged in. Sampling of that environment, such as the sampling performed on the International Space Station that we do now, will also be done to characterize the microbiome or changes to that microbiome. Advanced containment systems. Design and implement robust containment protocols for sample return missions, materials and biological samples, including astronaut waste, should undergo strict quarantine and decontamination procedures upon return to Earth. And then Earth-based Earth-based preparedness, establishing those partnerships with public health agencies, much like Dr. George mentioned, research institutions and private sector stakeholders to develop response strategies for any unforeseen microbial risks that we might have. There are additional recommendations that I would ask the committee to entertain as practical areas for consideration. These considerations or recommendations will seem familiar to you in the context of biosecurity and mirror several of the actions that currently occur when there is a biosecurity trigger. The first of those is to establish an expert panel and formation of a formal panel convened for meetings on an ad hoc basis to review plans and assess risk and safety to the public for any sample return missions and human-rated missions to other celestial bodies. The panel would consist of NASA's Planetary Protection Officer, NASA's Chief Health and Medical Officer, the NASA Science and Mission Directorate Associate Administrator, Assistant Secretary of ASPR, CDC Director or their designee, DHS Assistant Secretary of Science and Technology or their designee, and the White House OSTP representative or the Director of Pandemic Response from the White House or a similar role. The panel would review plans, risk mitigation strategies and safeguards for sample return or human mission return. The panel can invite recognized subject matter experts from academia as needed as well. Also, the sharing of lessons learned. NASA would convey its lessons learned and forward and backward protection to commercial entities and other international partner government entities. Now, this could be via public posting, via discussion or documentation at our United Nations Committee on Space Research or COSPAR, or Committee on the Peaceful Use of Outer Space meetings at the UN as well. Commercial oversight. NASA is not a regulatory body or agency, as you are all aware. It is recommended that a government entity, whether that's the FAA, Commerce, or another entity, be identified to assess the plans and risk mitigation strategies for commercial sample return or commercial human exploration missions. And for the brevity of time, and to give Nick plenty of time with his outstanding title of Planetary Defense, I'll stop there and see what questions we may have.
Take
So-
questions after.
I think we'll just take questions after you
Gotcha.
both speak. If that's okay. And then
Thanks.
you can
That's perfect.
tag team the answers.
Perfect. Okay, Governor Ridge, Madam Secretary, and members of the Bipartisan Committee on Biodefense, good morning, and I thank you for your invitation to brief you today on planetary protection and the importance of planetary protection, enabling science exploration activities, but perhaps more germane to this group, the prevention of adverse impacts to Earth's biosphere through sample return activities. Planetary protection objectives focus not only on enabling science, but on the safety of Earth's biosphere and from extraterrestrial sample return. These two objectives can be directly traced to the Outer Space Treaty of 1967 and Article 9 that denotes that state parties to the treaty shall produce studies of outer space, including the moon and celestial bodies, and conduct exploration of them as to avoid harmful contamination and also adverse changes in the environment of Earth resulting from introduction of extraterrestrial matter, and where necessary, adopt appropriate measures for this purpose. Within the discipline, we commonly refer to avoiding harmful contamination as forward planetary protection and avoiding adverse changes to the environment as back planetary protection. For your reference and consideration, I want to showcase the current policy pertaining to the planetary protection discipline. The Committee of Space Research has a panel of planetary protection that maintains the voluntary international consensus policy that provides guidance for commercial and space activities and agencies conducting space exploration. This COSPAR policy is a potential accepted means of compliance with the Outer Space Treaty of 1967. For NASA specifically, as an agency, we participate in COSPAR and use COSPAR as one of the means and sources to inform NASA planetary protection policies for NASA and NASA partnered missions. Each mission planetary protection risk is based on current scientific consensus of the potential of life and if space exploration activities could serve as an inoculation event for solar system targets. For forward planetary protection, we work closely with the astrobiology and planetary science communities to ensure that harmful probability of contamination from NASA activities is less than 1 × 10⁻⁴ by establishing factors such as the starting number of organisms sent on the spacecraft, the probability of an organism surviving, the probability of growth, and the probability of release. In addition to these factors, the discipline also balances sensitive science activities that are conducted on the mission. Design of experiments, limits of detection, and signal to noise drive this interface between science and planetary protection policy. One might think of this as a tripwire, where science maintains the standard design of experiments, but when there are implications between missions or for life detection, planetary protection becomes a possible stakeholder. Missions returning samples to Earth implement backward planetary protection fall in two categories. The first of those is unrestricted Earth return, like asteroids, where the science evidence is used to conclude that the target body does not have characteristics to harbor extraterrestrial life, or restricted Earth return, like Mars, where extraterrestrial life could be present due to water availability, temperature, or energy sources. For unrestricted Earth return, an evaluation of current science posture and mission documentation is required. For restricted Earth return missions, there is a presumption that samples contain hazardous biological material that must be contained until deemed safe. This also applies to crew missions we are planning to Mars, and the Office of Planetary Protection coordinates with the Chief Health and Medical Office, Dr. J.D. Polk's office, to coordinate these policies. To ensure that a high priority is placed on preventing adverse impacts to Earth's biosphere, samples from restricted return missions are subject to NASA policies and have been informed by Apollo lunar sample return and past studies with prominent subject matter experts in public health and biosafety. These include the National Academy of Science, Engineering, and Medicine, U.S. government department and agencies, inputs from the National Strategy of Planetary Protection, academia, and the medical sterilization community. Furthermore, since restricted sample return activities could have major and protracted effects on the biological environment, NASA has to consider Presidential Directive National Security Council number 25 in its mission approval process with engagement of the White House and Office of Science and Technology and Policy. To implement restricted sample return missions, NASA manages unsterilized particles through containment and/or sterilization and plans to house returned samples in a sample receiving facility that leverages both cleanroom and biocontainment protocols to not only protect the biosphere, but to ensure that samples are not contaminated from Earth to enable sensitive science. Currently, we are working with stakeholders across the U.S. government to ensure that practices and protocols are understood and state-of-the-art, leveraging expertise from organizations such as HHS, CDC for biocontainment, or DOT for transportation of biohazardous materials. To decide if samples can be released, there is a sample safety assessment framework published in Astrobiology by Kamenik et al. In 2022 that employs a Bayesian statistical framework in a multi-step process that factors in 3D structures, gas analysis, chemistry and mineralogy, organic molecules, molecular patterns, and macromolecules. As you can see, NASA has put a lot of care and detail into planning for restricted Earth return samples to ensure safety of the public and Earth's biosphere, actively working the topic, and is leveraging decades of experience. As far as recommendations for this committee, I would encourage the following. 1, engagement of NASA Planetary Protection for health and medical life detection expertise in determining sample safety and risk. Since Apollo restricted sample return, NASA has been coordinating and working sample return activities to determine sample containment, sterilization, and sample safety assessments. 2, participation of the biodefense community as part of the USG coordination for sample return activities. Given NASA's approval process for restricted return samples are governed by PDNSC 25, we have engaged the USG to help develop implementation approaches. If there are additional considerations or partnerships, we'd be interested in coordinating those further. And 3, leveraging the National Strategy of Planetary Protection or international standards for non-NASA missions. NASA policies are acceptable for NASA and NASA partner missions. Since NASA is not a regulatory agency, the National Strategy on Planetary Protection or Committee of Space Research Policy could be considered as a means of compliance. Thank you for your time and consideration of planetary protection.
Okay. Thanks both you gentlemen for your excellent points and your willingness to be here today and raise these issues for us. I'm a little bit new to this issue, so let me start with you, Nick. You mentioned a couple times that NASA is not a regulatory agency, and then you discussed, the various protocols. There's a framework, guidance, and policy, and the like that I guess sort of controls some of these restricted activities when they bring space material back to Earth. And I understand there's the treaty that I guess there are also guidelines for adherence to that treaty. Yep. My question really is triggered by your comments that NASA is not a regulatory agency. Is there a mechanism and an authority within the government to dictate not only to government actors, but to commercial private sector actors what must be done when coming back from space, such that, I mean, we have the federal government has the authority under the Constitution to regulate interstate commerce. I mean, if you regulate interstate commerce, for a variety of health and well-being reasons, presumably, Congress can do the same thing as it relates to travel between states, the space and Earth. Is there an authority to do that, and such that private actors need to submit to that authority? And well, that'd be the first question. And then how would you maybe revise that authority to make it more foolproof?
Yeah, so several years ago, we had the National Strategy of Planetary Protection that addressed both forward and back, as well as commercial objectives within that. As part of that effort, we had working groups, both for forward and back planetary protection across the interagency that worked through planetary protection processes for commercial players. One of the examples that came that we work with is our colleagues over at FAA as part of the voluntary payload launch licensing process. And that when a commercial entity submits a launch license, part of that is a potential evaluation for planetary protection, depends on where they're going. And so we, as a subject matter expert in planetary protection, serve to consult with the FAA upon request for any planetary protection concerns for those voluntary payload licenses. So.
Okay, but you use the word voluntary. So
correct.
Is that there's no sort of strict requirement that before a commercial entity decides to do a launch and then come back, that there be protocols that were accepted, that are approved?
So FAA is the launch license authority. So we work within their regulatory space and engage when needed.
Okay. And do you think that's sufficient as it stands?
I think overall that's a potential path forward that we have. We haven't seen any potential issues arise of that. Certainly, something that could be looked at further.
Okay. JD, anything more on that?
Probably not more to add on that other than what we see our role to be, which Nikki alluded to, even on the Chief Health and Medical Officer point, is to continue to educate the commercial entities. We've got 65 plus years of human spaceflight experience, and so it would it behooves us to educate them on our lessons learned. Some of those were hard lessons learned, and to make sure that the FAA and others that are going to take over that regulatory function have the lessons learned that we have, so that when they do promulgate any type of legislation or anything to cover those, that we give them the best evidence base.
Okay. All right. Thank you. All right. I'll go around the horn. Secretary Shalala.
Just a quick question. Dr. Polk, I appreciate the invitation. Biochemistry did me in. I wanted to ask about the information you have on the astronauts, because we're sending up people from different countries. Do you all test the same? Do you have the same information about their health? Because one of the concerns is that we're passing out diseases once they get up there.
Well, great question. First, we used to be very covert, if you will, about our selection standards because we didn't want somebody to game the system or know what we were looking for when we did selection of astronauts. We flipped the script on that with commercial spaceflight and our international partners. We decided we would share our selection standards. They're out on the web and the open right now. And part of that was so that all of our partners, international, commercial, otherwise, would learn from the NASA experience as to what do we have as selection or exclusion criteria when someone becomes an astronaut. And also we have our multilateral boards that we share with our international partners, all the testing and what we see and have seen on orbit. The difficulty that we've had in putting things in literature is that in order to maintain the privacy of the astronaut, you have to wait to have a large enough N number before you can publish it so that someone can't figure out who we're talking about necessarily. But we have shared many of those. But to your point about the shared collective microbiome, that's one thing that we have seen is when we test, especially the gut of an astronaut, there's a great deal of diversity before they fly. And it becomes much more homogeneous in that enclosed environment of the ISS after 6 months between all of the different astronauts. And so we're aware of the behavior of how that microbiome changes over time. And for that reason, we look for selective threats that might cause a harm to the community as a whole. I'll give a couple of examples. H. pylori, for example. H. pylori, we know on the ground causes stomach ulcers. On the ground, if you cough H. pylori, it rapidly falls to the ground thanks to gravity. But if you're on the International Space Station and you have H. pylori and you cough, that H. pylori is now floating in the atmosphere, waiting for your partner with their mouth open to come sailing through. And you can all have H. pylori inside of 2 months. So we look for things like that in the astronauts pre-flight and eliminate and treat or mitigate those risks so that we can mitigate the risk to the community. Although we do not have standards or requirements for the commercial or private astronauts, since we do not regulate them, if they are coming to the International Space Station, we do have requirements for them, and those are aimed almost exclusively at the biopreparedness and making sure that they don't bring something up that could harm our crew or our mission, TB, for example, or something else of that nature. And so we do test a great deal, whether that's looking for Neisseria in the nostrils, whether it's Staph aureus in the skin, throughout the astronauts before they fly, with that knowledge that shared microbiome could create a threat to the whole if it's not treated and addressed appropriately.
Thank you, Ken.
Okay, do we have Governor Ridge?
No, he stepped away.
He stepped away? Okay. All right. Senator Daschle?
Well, thank you both for outstanding presentations. I'd like to really just ask a very basic question that has intrigued me. If you could summarize the biological threat as we've now understood it to be over the past 60 years with all of the experiences in our space travel and astronaut training, how would you describe what that biological threat is today? And is there a greater threat going into space or coming back from space?
That's a great question.
If you could both address those two questions, I'd appreciate it.
Yeah, I'll start with your last question. Is it a threat going into space or coming back from space? The answer is yes. We do quarantine prior to the astronauts taking off because knowing that, a bacteria or virus may have an incubation period before it rises. We don't want an astronaut to be sick in space. If you go back to the Apollo 13 movie with Ken Mattingly being exposed to measles, there was a family that had measles, and just because of the potential for exposure there and the incubation period for measles, Ken got disqualified from that flight. And so we take that very seriously. And I have no doubt that there was robust discussion at NASA about grounding an astronaut for a potential exposure to measles. But we couldn't risk it because it would potentially harm the entire mission and the rest of the cadre that were on orbit. So pre-flight, absolutely. And that's one of the reasons that we have quarantine. We had to back up that quarantine several weeks with COVID. And then post-flight is also a risk. The astronauts, as I think in your publication noted, they do have some immune compromise. They have some T cell compromise. It's not massive, and it doesn't last very long. Those T cells respond back within a couple of weeks after return to Earth, but it's still there, and it creates a potential risk for them if they were exposed to members of the community or public that might be infectious. So we're wary of that as well. For exploratory missions going to Mars, the difficulty is you're going to take a human being with a lot of bacteria and viruses and fly them through microgravity and radiation to Mars, be on the surface of Mars for some period of time, and then fly back for 6 months to 8 months again. And so there is a risk there. But fortunately for us, Mars is far enough from Earth that when they do leave the surface, if they picked up something that was a contaminant in the Mars soil or elsewhere, that they're essentially isolated for 6 months in that spacecraft and in miniature quarantine, if you will, coming all the way back. And so that gives us the opportunity to do testing, evaluation, and surveillance of that microbiome and the astronaut's health on the way back to get an idea of what our risk is before they return to Earth.
Thank you. Dr. Benedini?
Yeah. Yeah, and I think to add to JD's points, really from a overall risk of back planetary protection, one of the key things we integrate is our planetary science knowledge on life as we know it on Earth and various analog environments here into that assessment. So we leverage a lot of the scientific consensus that's built along the way, getting impacts and inputs from national academies and others to allow us to start to think about the types of risk that may be present. So for example, if we go to the equator of Mars and we're at the surface, that's probably less risky because we know that it's high UV intensity. For example, lots of biocidal potential impacts that could help mitigate some of the risk. Whereas if we go and are thinking about, for example, Mars exploration, where we're digging below the surface, where galactic cosmic rays and UV doesn't penetrate, then that risk goes up. So we weigh those potential biocidal factors against what we're up against to try to understand what we need to mitigate for our various mission scenarios and architectures. But yeah, very much as JD pointed out, we use kind of that first astronauts boots on the ground as kind of the canary in the coal mine, and using that kind of 6-month period coming back to help inform us and being able to do that biosurveillance along the way to understand any impacts as part of that mitigation strategy that we're planning.
Well, thank you both.
Okay, Jim?
Thank you. Question for Dr. Polk. I read in the pre-reads that a couple of things. One of them was that being, I guess, weightless can cause viral shedding to increase. Is that correct?
Yes.
Right. And then you talked about the fact that maybe with that shedding and then the weightlessness that those microorganisms can be in the atmosphere. And my assumption is that that could be a problem for the astronauts while they're aboard, but it's not necessarily a problem with them coming back, and they're the same microorganisms that were with them when they were walking around. But what is there a danger of those microorganisms mutating because of the environment in which they are, and then becoming, more contagious or more harmful on return?
Yeah, and I would separate this based on what we see on the bench for basic science research versus what I see clinically. We know through multiple different studies that we have increased viral shedding, Epstein-Barr virus, herpes viruses, et cetera. Whether that's due to the stress of spaceflight, microgravity, radiation, I can't tell you exactly what the potential cause of that is. However, I don't have runaway herpes viruses or zoster on orbit. I have not seen a translation from that viral shedding to clinical disease. However, it does inform our clinical practice guidelines, and that we didn't, when we saw all of this increased viral shedding, we decided, most people don't get their Shingrix vaccine till 60 and over. We're giving it to the astronauts at a much younger age because we know they're going to have viral shedding. And so part of that is I'm preventing the clinical disease because I am well informed about the behavior of those viruses on orbit. So I have changed or mitigated that risk up front before they ever leave Earth. But to your latter point, anytime you have subjected bacteria or viruses to high energy transfer particles like galactic cosmic radiation, microgravity, other different and host environments, the moisture and humidity of the ISS, any of those areas, we have seen increased virulence of bacteria and viruses. But again, that's
in experiments, is that right?
Experiment,
Not
yeah.
from the astronauts themselves.
Fortunately, knock on, where's my wood? Not in the astronauts. And I think that brings about a very important data point. To date, in 65 years of human spaceflight, I've not had to return an astronaut once for a medical reason. We have treated plenty of things on orbit, but every model has said we'd have to return at least once every 3 years, and so far we have not had to do that. And I think that is due to a massive amount of diligence on the part of NASA throughout the years, and heightened awareness as to the changes in that microbiome and the risks that are in spaceflight.
Thank you. And Dr. Bernardino, in thinking about the project to go to Mars and bring back material from Mars to Earth, what kind of microorganisms that exist on Earth could also exist in such a harsh environment as Mars? And then in reverse, what kind of microorganisms might in fact be on Mars that could in fact come back and exist and survive on Earth?
Yeah. So to start with the latter, that's the billion-dollar question, and what we're setting out to do. Quite frankly, we know that there's a lot of Mars conditions that could allow for life as we know it on Earth today, and quite simply, that's what we're set out to do and to go explore, to bring those samples back to understand that further. But to your first point. We actually, for forward planetary protection, leverage bacillus spores as kind of our sentinel organism, if you will, for what could potentially survive on Mars and through the treatments that we use for our spacecraft surfaces. So a lot of our forward bio management protocols and requirements are based on bacterial spore, what we can do to decontaminate our spacecraft and microbial reduce it through a series of dry heat microbial reductions, solvent cleaning, et cetera. And then likewise, being able to assess that cleanliness before launch itself. We know that a lot of those spores serve very well for bioindicators on a lot of our dry heat microbial reduction studies. For example, we originally used some of the early Department of Health studies for our heat microbial reduction until we found a higher heat tolerant organism actually from our spacecraft during the Viking processing stage. So we were able to kind of up the bar, as it were, to increase our time at temperature for microbial sterilization, getting to the Martian surface, or getting the spacecraft prep to go to Mars. Likewise, we do a lot of Mars ground-based simulations using these spores. So we know that using the multivariate factors, desiccation, deep space vacuum, and dry heat microbial reduction, irradiance with UV. We know that these spores survive very challenged environments similar to Mars. So we're able to think about leveraging those in our models for microbial decontamination and being able to apply those biocidal credits to how organisms might survive on Mars and build that on our ground testing to date. So.
Thank you.
Fred?
Well, thank you both. I've got just a couple of small questions. You talked a little bit about the international treaty that the U.S. is part of. Is there any country that's involved in the space program that has not ratified that treaty?
You know, I can't say.
I mean,
off the
I know
top of my
India, I'm
head.
just thinking
Yeah.
Japan, Russia, China.
Yeah, I can't, you know, as we look at our partners, we've got the partners that we work with intimately, and then we have additional partners that are providing hardware and
Right.
others. I'm not, when we say is there anyone that is currently working with NASA or with on the particular programs that is a signatory, you know, when you look at the Artemis Accords, that's quite a few countries. I'd have to go back and look almost line by line to see who's a
I just
signatory
wanted-
not there. So I wouldn't be able to answer that with great.
And then our partners that, I mean, you look at SpaceX, you look at Boeing and others, I mean, they're fully engaged and working, I would guess, right?
They're fully engaged if especially if they're working with us, because our requirements and standards apply to them if they're working on a NASA mission. And I think that's an important point there between that and commercial or private missions.
I know in most cases, an asteroid, when it comes in and gets into the Earth's atmosphere and ultimately to the Earth, I mean, it's very seldom are you actually going to have a team that's going to be there to measure the gas or whatever it might be. What about, I know this week I read that a Russian spacecraft that has been up for some 50 years is coming down in the next couple of days. And it's pretty large. Is there a log? I mean, I don't know if this is nuclear. I mean, I don't know if it's nuclear powered or whatever, but is there some log or list of the potential hazardous materials that might be on that's available for countries to know if in fact it lands, you know, your backyard?
Yeah, I'll defer to Nick since there's no humans on board
Yeah.
that spacecraft, but we do know that Space Command certainly keeps track of all of those objects. And
But
we
do the Russians
share.
and other countries, I mean, do they publish, you know, this is lithium battery, I mean, whatever, nuclear or whatever, I mean,
Yeah.
is there an identifiable list?
So from a planetary protection standpoint, the Committee of Space Research actually has about 17 spacefaring nations. Russia, China notably participate as well on this, where they report activities that on their spacecraft that involve planetary protection forward and back issues. And so they have meetings twice a year where each of the agencies can report their activities. So that's one of the means in which we get updates on the various missions that all of our nations are conducting. So
Is there a, so, you know, 65 years of space exploration, to date, have they identified anything that's been harmful that's come back?
not to my knowledge.
And you indicated that you in fact have treated astronauts without violating HIPAA.
Mhm.
What are some of the things that you've treated them for? I mean, I presume are they taking up Tylenol and a leave? I mean, what's in the medicine cabinet?
Right.
that they've
Well,
got?
you know, that medicine cabinet is robust, but we divide kind of the medical hardware into what you might have, you know, in your cabinet at home, Tylenol, Aleve, things of that nature. And then we have the emergency medications and other medications that require obviously a lot of discussion with the flight surgeon and the crew. And we divide it in those two forms. And so, but we don't guess what we're going to take up. We do a great deal of study and analysis, what's called a modified Delphi and other things to decide what medications we're going to take up. Part of that is due to our experience and what we know we've treated in the past. Part of it is looking at what we have seen in analogs when we've done analog missions. Part of that is comparison with the Navy and benchmarking off the Navy nuclear submarines and what they have treated in an enclosed environment in their community as well. And so we take all of that information to divine what we are going to fly. And so it's, common things occur commonly. Sometimes it's
Ice packs are got to be pretty easy, right?
yeah, well, sometimes it's just, somebody gets a dental carie and, we can't bring them down and go to the dentist on Tuesday. And so it might be treating that dental carie for a while, although we try to make sure they don't have any before they fly. Things do happen. Other more important or serious things that we've seen probably relate to the microgravity and the changing of fluids into the head and thorax and brain. But from the infectious disease standpoint, skin infections that we've seen or other things, they've been small, trivial things that you would probably see or would treat at an urgent care or go see your family practitioner for. But we've not had, what I would call serious infectious diseases. We have not had meningitis. We've not had, pneumonia, things of that nature. With that fluid shift, though, you can get pretty stuffy with suddenly all that fluid that's been sitting in your lower extremities now being up here. So sinus is not an uncommon thing for us to treat initially. And so those are just the types of things that we see.
Okay. Well, thank you. Thank you.
Donald?
Just a quick question. I've always wanted to ask this. Has the International Space Station ever had a mold problem?
It's not unlike any home in the United States where you're gotta constantly keep after it because of the humidity and other things that we see. Although we have the air generation and filters throughout the ISS, you get pockets of areas that might have more humidity or moisture, especially if you've got a water spigot there or other things for food or for drink or other hygiene and other aspects. And so the crew, one of their tasks, the career of astronaut sounds glorious until folks figure out they actually have to do a lot of cleaning on the weekends. And so they're maintaining their home just as we are to keep the mold at bay.
Thank you.
New idea for a 409 advertising campaign. All right, Asha?
Just a few questions. JD, one of the things that we've been talking about is new technology, relatively new technology. People have been talking about the use of 3D printers to assist with not just technology, but possibly medications. Have you guys thought about that? And or are you already utilizing that for the medical care for the astronauts?
Yeah, that's a great question. And part of that has to do with what we call the 6 tenets of spaceflight and space medicine: mass, power, volume, time, money, and risk. Folks will say on the ground, well, are you going to take a CAT scan? Well, no, it's huge. It takes a lot of energy, a lot of mass, a lot of volume. And same with pharmaceuticals. Am I going to take the entire CVS or Walgreens with me to Mars? Well, the program's not going to give me that kind of mass, volume, or budget to do that. And so we've looked at, could you do just-in-time medications? Could you actually bioprint a medication if you need a Cipro or a Zithromax? And we've worked with several universities. University College London, for example, has one where they are bioprinting or doing 3D printing of medications. And if you think about the construct of most medications, the acronym SHNOPS, and I don't mean the drink from college, I mean more carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Almost all of the medications we have in the stockpile and elsewhere are those chemicals in some form or fashion. If you go back to Secretary Shalala's beloved biochemistry, when you put all of those together, if you know the recipe, you can probably print out a pharmaceutical if you know how those constituent chemicals go together. And so it would be a big savings in mass, power, and volume for me to take constituent chemicals and then in a just-in-time fashion print a Cipro or a Zithromax or things of that nature. Right now, the technology is to where they already have a ready-made tube of medication, of Cipro or et cetera. And then the 3D printer is spritzing out a 500 milligram dose. So it's not quite where we need it to be, to where you would formulate those chemicals. They're already pre-formulated and it's spritzing much like you would a cookie onto the cookie cutter or onto the baking sheet. And we needed to go a little bit further, and we call those TRL levels, technology readiness levels. But we're working with the different pharmaceutical companies who I think envision not only its usefulness in spaceflight, but how that would also translate to the ground, and especially in third world countries or others, to where, if you had the ability to on demand 3D print medications with just the constituent chemicals. So that is something that we are looking at.
Okay. Nick, when we talk about planetary protection and the idea of possibly bringing something back, we don't, at least I don't think we should be assuming that what we have here on Earth is what we're absolutely going to see on some other planet. But this raises a challenge in terms of diagnostics. Have you thought about that? Because what you don't want is what I said earlier, the human sentinel system, where people are coming back and now they're getting sick and you have an organism, you don't know what the organism is. It's going to have implications for treatment, but it's also going to have implications in terms of planetary protection coming back to us.
Yeah, so I see you have Michael Meyer on your agenda coming up, so he can talk a little bit more about the specific science details here. But one of the things we do is we coordinated highly with the science community in trying to understand what potential science would be done for understanding what they would want to do on the sample return. So there's a whole series of efforts for both the sample safety assessment for planetary protection that basically determines whether or not we keep that in containment or we release it out. That, as it stands, is a whole set of Bayesian statistical framework, as I mentioned earlier, that looks at everything from macromolecules to gas headspace and trying to understand as soon as we can what is the possible threat of that sample, so we can make a determination whether or not we can release that out to the broader scientific community quicker, or we need to do some more analysis. And so that is a very much published framework with an ever-evolving protocol, because as you know, science is changing every day. So we definitely want to ensure that we are engaging and continuing to engage the science community on this up until when those samples come back, which is, decade out plus. So we want to make sure that we're able to, get the most updated science in coordination with the efforts that we're planning for a sample receiving facility and where those instruments and capabilities would be within that facility.
Okay. And then my last question is just kind of a minor one. You mentioned OSTP. I know there's some interaction, of course, with the National Security Council when it comes to the maybe the classified stuff. But there is a National Space Council up at the White House as well. Is there a lot of interest from them or, well, maybe not interest, but responsibility?
Yeah, so National Space Council was part of the National Strategy of Planetary Protection. And so they were engaged throughout that process during those working groups.
Okay. Thank you.
Okay. Ms. Hughes, any questions?
I do. Thank you. Absolutely fascinating testimony, both of you. I was interested particularly in Dr. Polk's mention of a microorganism that had become more virulent in space. And I understand from the readings that we were provided by our staff that there have been different studies that have been done in the past several years looking exactly for those kinds of issues. And a researcher from my home institution actually published a study where she found that there was increased virulence in an organism that, and it may have been Salmonella, but I don't recall what it was. Cheryl Nickerson was the researcher, but there have been a number of different studies. I saw that there's the GEARS study that was started about a year ago, looking at Enterococcus faecalis. Another one that's older than that, where it says that there were, in a survey of bacteria on station, 13 strains of multi-drug resistant Enterobacter burgundensis, which is not familiar to me, that were found to have mutated to become more resistant to antimicrobial treatments. And that sounds dangerous. I'm sure that they're in sealed environments, and so that the astronauts are not going to be exposed to them. But I wonder more broadly about research that's done on station, on ISS. And I know you get studies that are sent up from students, all kinds of possible opportunities, and that there is, as you'd mentioned, very careful cleaning after they return. But is that something, and, you know, the fact that you have another study that was started last year means to me that you still have this continuing concern that something might be brought back. It could be something that went up and became more virulent or mutated in some way. How are you dealing with that now? And especially because it's an international space station, there are astronauts and facilities that come back and go to other countries once they return.
So just to start out, and then I'll kick it over to JD. We're leveraging the ISS right now to understand and apply requirements on biosurveillance and monitoring, particularly as we think about going to Mars. We want to make sure that we have those systems dialed in and really trying to understand how that changes throughout the course of the built environment that our astronauts are in. And so we have a series of knowledge gaps that we've identified for planetary protection, of which microbial monitoring and surveillance are needed to address and mitigate some of that risk for the astronauts. And so some of the work that we're doing, as you mentioned, directly relate to that of just understanding what's there and what role are they playing in that environment. And we've also started over the past couple months actually sampling the exteriors of these environments as well, because potentially there could be possibly hardy things surviving on the outside that have vented out through the built environment that would also be of potential interest to understand. So we've done a series of swabs, getting ready to do some more as well, but I'll let you speak.
No, your memory's quite good. It's Salmonella enterica typherium from your home state that we had looked at. And I think there's a couple things that we have seen. One, that the stress of spaceflight, and I wish I could tell you whether it's directly related to radiation or if it's microgravity environment or the enclosed environment of ISS. But we see that there are chromosomes that turn on and off. And actually globally, even on the astronauts, if you think about the experiment, the twin study that we did with Mark Kelly and Scott Kelly and comparing identical twins, the stress of spaceflight had turned on certain chromosomes with Scott rather that had not turned on with Mark when we had compared things. But that happens to us on the ground as well. I mean, if I have not been exercising for 30 years and suddenly become religious about exercise, I'm going to start to turn on certain genomes. And you know, the question is, when do they tip over into pathology? And so right now we're able to see the behavior. And also that helps us to identify potential methods for mitigation, whether or not these changes in the speciation or the behavior of these different bacteria, you know, does it change their reception to alcohol, benzalkonium chloride, or hydrogen peroxide, or other decontaminant materials. And so that helps us also to try to figure out, based on what we see, what is the best way to mitigate risk in the future. So we see that behavior, but again, like I had mentioned earlier, we have not seen it tip over into clinical disease yet. But it still heightens our awareness for the potential risk for planetary protection. And that begets a lot of other research that we do looking at the mitigations for that, whether that's HEPA filtration and getting in a smaller micron and HEPA filtration in the vehicle itself, whether that's the cleaning agents that we may use in the vehicle, or whether that's bedside sampling of the astronauts as well. And if there is maybe a silver lining to the pandemic, it is that it did move technology forward on bedside testing for things of microbiological or viral nature.
Thank you.
Yeah, I have a couple of questions for both of you, but my first question is for Dr. Polk only. Are you related to the president of the same name?
I am. He and Sarah did not have any children, but he was one of 11 children, so I'm related to his brother William. And by the way, President Polk also died of cholera, so he's kind of, it's a good person to talk about in a biodefense forum right now. He did not have adequate mitigations for biodefense when he did his post-presidential tour of New Orleans.
Yeah, thank you. It was a combination of cholera and overwork. He did not take a single vacation while he was president.
Yeah.
So my question for both of you is, you said that there have been no contaminations that have taken place in the 65 years or so of space travel. Does that mean that there are no contaminations have happened because of the strict protocols you discuss, or because perhaps the threat is not as great as we fear? And then related to that is, what is the biggest contamination that you worry about late at night?
Yeah, and let me clarify, in the 65 years, we've not had to return from space for a medical reason, but we have had contaminations in what we would call our crew health stabilization program, but the measles that Ken Mattingly might have been exposed to, but fortunately was not. We've had violations of other things in the crew health stabilization protocol. Have we had an astronaut, come down with a cold or something while within a day or two of entering quarantine? Those things have occurred. But I haven't had frank disease from any of the increase in viral shedding or the changes in bacterial virulence on orbit. But that doesn't mean that I couldn't in the future. But a lot of that has to do with a lot of the mitigations that we put on board right now. And of course, we look at the astronauts and speak to them once a week in our private medical conference. They are a highly surveilled population. But that will change when you get to Mars. It's 20 minutes one-way communication. There'll be comm losses as they're going around the sun. They'll be much more autonomous. And so I think that's the important part of learning the behavior of many of these microbiomes and the ISS environment right now, and also our work that will take place on the moon, which is only a short distance away, before we get to Mars, where it's going to be much more autonomous, and we'll have to rely on the crew themselves to do a lot of the diagnostic acumen and keep their threats at bay.
Thank you.
And then from a sample return perspective, I would say that our risk assessment from the scientific community feeds very conservative data points into their current policy of how we govern and think about sample return. That's why we have unrestricted. So think, asteroids. We do this all the time, seemingly several times a year now, bringing samples back. And that community has gone through a rigorous set of and making sure that we have an international consensus standard for those target bodies that is very clear of the types of potential for not having life. So for example, if an asteroid's been heated to high temperatures that would denature life as we know it, then we know that there's no life there. And so we can leverage those planetary science inputs to inform us on the types of material that we would want to return from space. And so that very much plays into our policies. And then where we have unknowns, we take that conservative approach, similar to what we did with Apollo, and now what we're looking at with Mars, where there is potential for life or a higher amount of uncertainty. We then enact that restricted Earth return procedures with containment, sterilization, sample safety assessment protocols, et cetera.
Thank you.
So we have only 2 minutes left. Do you have a quick question?
Very quick, either for now or later. I don't personally spend much time in space, but I was wondering, you're interested and excessively informed observers. Do you have any comments to make now or on for later on earthbound biodefense in America?
No comment.
You can set aside your hats, you know.
No, not that I can think of at the moment, other than I think, it's like we've talked about previously. NASA in the past has learned its lessons for use at NASA. And I think we are increasingly in an educational role. We'll do the best that we can to educate those populations going to space, whether we are regulatory or not, because all boats float with a rising tide, and we want to see everybody safe in space. That's probably the best strategy that I can imagine right now. But I don't know if that really answers your question, but that's my tactic that we would take.
Okay. Well, look, thank you. Thanks to both of you. Tremendous insights and remarks. And I was very glad, actually, after going on about how cool your title was, Dr. Bernardini. I was so glad to hear that you have a presidential pedigree that gives you bragging rights too. So both cool in your own respects. But thank you. You all are both thought leaders in this area, and we benefit a lot from having you here today. And we would, per Scooter's question, if you have further comments about spacebound or earthbound biodefense, love to hear it.
The logistical scale and challenges associated with these types of projects are, of course, not identical to those related to the exploration of worlds outside of Earth. There are lessons learned that can help inform our actions now. So I'd like to provide a few conceptual examples here with some transferability to planetary protection. Our work has shown that the diversity of microbial life in a subglacial lake can rival that of a more typical surface environment. This tells us that despite the fact that subglacial lakes should be a very difficult place to live, many different types of microbes are able to survive there, a testament to the tenacity of microbial life. We know that Earth life can survive in these naturally challenging environments, as well as when subjected to experimental conditions similar to those found on other worlds. Therefore, we must prepare for the possibility that transplanted life could survive and perhaps grow outside of Earth, or that life from elsewhere could grow on Earth. And importantly, the fact that such capacities may not be rare. One major challenge that we face is that many microorganisms resist cultivation, meaning that we know that they're present in the environment because we can detect their DNA. But they have not been grown in a lab. Without a living specimen to study, we must make inferences about their capabilities based on genetic data. Even this is limited by our ability to correctly annotate the functions of genes that we find in the environment. If a gene is too different from one that's already been characterized, we have little idea of what its function might be. Together, these limitations around the cultivation of microorganisms and the identification of genetic function leave us ill-prepared to proactively assess risks associated with microbial life. We can address this challenge by supporting concerted efforts aimed at both the cultivation of new organisms and the development of new modeling approaches using, for example, machine learning, that show promise in identifying genes that might confer capacities that promote survival or growth in challenging environments, but that differ from modalities that are already known. Such methods are still new and must be used and validated judiciously, but show promise for important expansion of what is known. The approaches that I have just mentioned, however, are inherently reductive. They attempt to isolate a single organism or a single gene
to better understand its capacity and translate that to predictive power.
I also submit that activities that we are interested in, such as survival, growth, or virulence, are capacities that may be better characterized as emergent properties. These are properties that cannot be understood by reducing them to their individual components and that arise from interactions, so may occur as a function of sets of factors that cannot be identified a priori. This space is perhaps where the greatest risk lies, because what we think we know may not be enough to appropriately target our efforts and reduce vulnerability. I suggest that we need to combine reductionist approaches and targeted surveillance with continued analysis of natural and synthetic microbial systems in order to better understand where threats might appear from. In this way, we can build and maintain the flexibility and resilience in our preparedness and response systems that we will need to address emerging threats both on Earth and elsewhere. Finally, another major challenge is determining the implementation space for any proposed approach. What I mean by this is that, for example, when we first accessed subglacial Lake Whillans in Antarctica, we knew that the lake was situated at the end of a hydrological flow path. We knew where the water in the lake would go next. This allowed us to consider the landscape itself in our risk mitigation plan. So in addition to following careful cleaning procedures prior to entering the lake, we could weigh the consequences of an accidental release into the environment. Applying similar logic to planetary protection, we should carefully assess any location to be visited with regard for its connectivity to potentially habitable environments. This would serve to protect both the environment being visited and any materials that humans might interact with, either on site or upon return to Earth. Thank you.
Thank you. Next, we'll hear from Dr. Robert Lindbergh, who previously served as vice president of two small space companies, Moon Express and Vector Launch. Welcome. Thank you for your work.
Thank you, commissioners. Today, I'd like to talk to planetary protection policy as it stands within the United States, and particularly as it applies or does not apply to commercial space activities that we anticipate in the future. From the NASA panel, you heard that Article 9 of the Outer Space Treaty is the foundation for our obligation to protect other planets from biological contamination and protect the Earth from potential biological contamination of returned samples or returned individuals. Article 6 of that treaty establishes an obligation for all the signatories to authorize and monitor the activities of non-governmental entities in the context of the other obligations within the Outer Space Treaty. Historically, planetary protection has been a NASA domain, and that's been because NASA has been leading the planetary exploration programs for the United States. This is changing, obviously, with emerging interest right now in lunar missions that are commercially initiated, and eventually Mars missions that are commercially initiated. NASA's planetary protection policy, as Dr. Benedini explained, is only applicable to NASA. NASA imposes that on other participants in NASA programs, but if a program is purely commercial, then NASA has no ability to apply the planetary protection requirements. And since it's not a regulatory agency, there's a regulatory gap in need for a regulatory authority within the United States to regulate non-commercial or non-NASA, non-government activity. Nick also talked a little bit about how it's handled today. The FAA reviews commercially launched missions to determine whether the payload operator has obtained all the licenses, authorizations, and permits it requires. The review also determines whether the proposed mission can jeopardize public health or safety of property, U.S. national security or foreign policy interests, or the interests of obligations, international obligations of the United States. As part of that review, it consults with several other agencies, including NASA. NASA's Office of Planetary Protection Policy is consulted for planetary missions, but adherence to NASA or to COSPAR, the international policy, is not explicitly required. NASA's role is to comment on the existence or the lack of adequate planetary protection measures for such a mission, and it's left to the interagency review team to determine what action to take. Given the current situation, one step that can be taken without legislative or executive action is for NASA to more consistently insist on planetary protection compliance whenever NASA is in a supporting role on a non-governmental mission. So if a commercial mission comes forward and has a purely commercial mission to Mars, but they'd like to use the NASA Deep Space Network for communication with their spacecraft, then NASA can, through its agreement with that private party, insist on compliance with NASA or COSPAR policy as part of NASA's participation in that mission. That's an issue that doesn't, it's not a burden on Dr. Bernardini's office. It's a burden on the contracts organization within NASA to make sure that those are specified. But the bigger issue is that we don't have a regulatory agency with the responsibility to authorize and continuously supervise non-government activities. In 2023, the previous administration and the 118th Congress each proposed legislation authorizing the supervision of space missions of non-governmental entities. National Space Council proposed legislation to update the current law by granting the Department of Commerce and the Department of Transportation additional authorities to oversee novel space activities. On the congressional side, the Commercial Space Act of 2023, which was H.R. 6131, was introduced and considered by the full committee in November 2023. In contrast to the National Space Council proposal, the bill found that the U.S. government's existing authorization and supervision mechanisms comply with Article 6 of the Outer Space Treaty, but that the bill can clarify misperceptions of legal uncertainty and relieve administrative burdens on non-governmental entities. To achieve those objectives, the bill empowered the Secretary of Commerce to issue certifications for the operation of a space object and granted the Secretary the exclusive authority for the determination of international obligations. The Secretary may deny an application if the Secretary determines that the object's operation would violate U.S. obligation under the Outer Space Treaty based on clear and convincing evidence. Both pieces of proposed legislation have flaws with respect to planetary protection. Since H.R. 6131 could become the basis for new legislation in the current Congress, I'll focus on my concerns with the provisions of that bill. First, it instructs the federal government to interpret the Outer Space Treaty in a manner that minimizes regulation on the freedom of U.S. government, non-governmental entities to explore and use space that freely promotes space enterprise. The bill also provides that the non-governmental entities, quote, reasonably commercially available efforts are presumed sufficient for U.S. compliance with Article 6. Absent, and quoting again, absent clear and convincing evidence to the contrary. Both of these provisions might create problems for the international rules that the United States and other countries use to interpret treaties. In addition, the reasonably commercially available provision could raise tensions between the currently accepted NASA and internationally COSPAR policies and what constitutes reasonably available commercial effort. The reasonably commercially available standard could create less stringent planetary protection measures for non-governmental activities than NASA applies to government missions, and thus not achieve equal application of measures identified as a central principle in planetary protection science, policy, and law. So my second recommendation is that Congress should pass legislation to authorize the Department of Commerce or other appropriate regulatory agency the authority to regulate robotic and human planetary missions conducted by non-governmental entities. The agency should be granted the authority to develop regulations to assure compliance with the Outer Space Treaty, including continuous supervision of such licensed activities. The method of compliance should be consistent with NASA and COSPAR planetary protection policy so as to assure that non-governmental entities are held to the same standard as NASA and other spacefaring nations. My final comment has to do with the underlying authority by which NASA developed planetary protection policy in the first place, and that goes back to Presidential Directive NSC 25, which Nick mentioned previously. That was written in 1977. It's 48 years later. It is still the foundation for how we would deal with biological materials coming back to Earth. Its scope is much broader. It deals with large-scale scientific or technological experiments that might have major and protracted effects on the physical or biological environment. In 2018, an ad hoc committee of the National Academies examined the current state of planetary protection policy within NASA and noted that the government process to oversee samples returned from Mars and elsewhere originates in the Apollo era and is out of date. So my third recommendation is that the administration, most probably through NASA, most probably through the National Space Council, the National Security Council, and the Office of Science and Technology Policy, should revisit Presidential Directive NSC 25 in light of NASA's plans for Mars sample return missions and commercial interest in robotic and human missions to Mars. It's that presidential directive that would provide the foundation for the consultative panel, the interagency consultative panel that Dr. Polk alluded to in his remarks. With that, concludes my prepared remarks. Thank you.
Well, thank you. Our final panelist is Dr. Ann Cheever, who is a Technology and Security Policy Fellow at RAND, where she provides technology expertise and federal government experience in critical and emerging technology, including national security and policy. She's also currently the Space Biodefense Advisor at Rhodium Scientific. So welcome.
Thank you. Thank you, everyone, for having me. This is really exciting to be here and talk about three of my favorite topics: space, biotech, and biodefense.
Sports.
Sports?
Yeah.
There's another S in there. Yeah. Oh, and just to let you know, I did go to high school in Michigan, so formative years. There you go. So thanks again. I wanted to kind of pull a thread a little bit about my background before I jump in. So back in 2020, I was hired as a program manager at DARPA. The interview pitch, so to get hired, you have to have a pitch, and you give that to the technical office. My pitch was creating a biodefense and biosurveillance infrastructure for space. So fast forward a little bit, it didn't end up becoming a program, but a space program did come out of that. And then back up even before 2020 as an LB fellow, so Emerging Leader in Biosecurity Initiative, they held a Shark Tank for all of the fellows. And the Shark Tank pitch was Astrobiodefense. So I have this recurring theme of Astrobiodefense throughout my career. And this is the first opportunity that I've been able to actually talk about it and kind of bring it full circle. So thank you for that. So I'm going to start with a thesis, and then I'll kind of go into my three prongs that support that thesis and why I think it should be a way forward. When it comes to astrobiodefense, what it really needs, it needs to be full speed ahead on biotech innovation for space. And so most of my comments are kind of coming from a place where commercial innovation, I think, is the key and something we really need to focus on and push. And so we can't do biodefense, we can't do astrobiodefense or astrobiosurveillance without investing in biotech and infrastructure and the actual hardware and equipment that we need to do it. So with that comes investment. I don't mean investment just in dollars, I mean in time and focus and discussion and just talking to commercial space industry about the need for this, because ultimately it's good for them. It's good for their bottom line. It's good for business. They're going to need to actually focus on biodefense in space to do what they want to do. These commercial LEO destinations, they want to have a business model. They want to have a commercial product that means humans at some point will be in space. So backing up a little bit back to my DARPA time, DARPA is an interesting place. So you go there with a vision, and oftentimes you're looking over the horizon at a capability and a thing that we need to do, and you're pulling that into the present and building capabilities to accomplish it now. So it's very much over the horizon, thinking forward on what are we going to need. And for me, I was thinking about biotech. I was thinking about biosecurity. Most of my career has been, those two things. I'm a scientist at heart, but biosecurity has been most of my career, national security. So, and biomanufacturing. So what does the DoD need in space in the future? And what it came down to was a sustainment capability and an ability to actually sustain a presence in space. And so to do that, what Be Sure was the program that I settled on, and what I ultimately pitched and ran at DARPA stands for Biomanufacturing Survival Utility Reliability Beyond Earth. And the program was meant to answer the question, can microbes be engineered to be a stable, sustainable source of manufacturing in space? Microbes evolved here on Earth. They're bound by many of Earth's rules. When you put them in space, they do interesting things. They evolve and they mutate, and there are a lot of selective pressures on them. And Trista, was very eloquent in her thoughts about how that happens here on Earth. Space is a different environment. There are selective pressures there that I don't believe fully understand. And so Be Sure was meant to actually engineer those microbes, industrial microbial chassis. So we use them here on Earth for biomanufacturing. They've been proven to make products, industrial products, therapeutics, different things here on Earth. Can we take those and engineer them for a space environment? And so the program set out to do that. There were three technical areas. One was, can we engineer microbes to produce a product in the presence of radiation, galactic cosmic radiation? Can we actually hit them with radiation and still rely on them to produce a product? Can we alter the gravity that they function under and still rely on them to produce a product? And then the third prong was alternative feedstocks. In a closed loop system in space, you're not going to be able to rely on a launch of glucose to feed a microbe. Can you use CO2 or human waste products or other feed sources that you can find in space to use? And so that was the program. And ultimately, the program, we funded different teams. University of Florida, Rhodium Scientific was our payload integrator. UT Austin was another one of our teams looking at radiation. Washington University in St. Louis was looking at alternative feedstocks, and Space Tango was another company doing a lot of our modeling and techno-economic analysis. And so with that team, that very multidisciplinary team put together, we set out to answer that question. Can you use microbes to do things in space? Along the way, and the reason it's relevant here is that we learned a lot about microbial evolution or not, because we didn't want them to evolve in space. We wanted all these selective pressures, and we don't want them to do a thing because they have to do what their job is, which is produce a product. And so, it's an interesting almost counterweight to what we've been talking about in terms of microbial evolution. Like, how do you not have microbes evolve? So that was Be Sure. And there's a lot more there to unpack, but I wanted to kind of go through kind of the three things that I think are really important here. And one is to promote the US space economy and the potential, the massive potential that the US space economy has in space. Anything from tissue engineering and biomanufacturing, stem cell aging, all of the things that the NASA INSPA program has funded, all of these projects that they've shown amazing results about. And so, and I've seen it's at Space Symposium, the commercial sector is enormous there. What is lacking in a lot of these conversations is biodefense. Like, what are you going to do when you're up there and, and things are changing? What is that? How's it going to affect your business? So we need to have those conversations. The second thing is to invest in increase innovation in biotech. That starts here on Earth in bioindustrial and biotechnological investments here on Earth so that they can be translated into a space environment. I know I said that it's going to require a whole new and different infrastructure for biosurveillance in space, but it does have to start here on Earth in those investments and conversations. And then thirdly, I spent the last year on the National Security Council at the White House. And so I saw in my portfolio, there was biotech. So it was biotech innovation and US leadership and global allies and partners, and how do we promote the bioeconomy? And so, there it was interesting. The directorate I was in was technology and national security. So we did AI, we did quantum, we did biotech, we did semiconductors. But what we didn't do was anything outside of that. It was very narrow focus on terrestrial biotech and bioeconomy, which was fine. That's the purview. But I didn't know where else to go in the NSC to actually have those integrative conversations. Pound defense, everything space, everything defense, but no biotech, no bio, no actual, biodefense or anything else related. And so I think structurally, OSTP, it lives there, definitely lives there. But they have different superpowers in the NSC. And so I think there needs to be some sort of counterpart or some sort of more crosstalk when it comes to astro, biotech, and biodefense. And I know I'm out of time. So those are kind of the three things, and happy to unpack them more.
Well, thank all of you, for sure. And at this point, we'll do a little Q&A. Dr. Cheever, you talked about your number 2 priority was invest in innovations in biotech. What happens in each of your perspectives in terms of where you've done? You see the federal government cutting back funds on a whole number of different things. How does that impact your specific role in terms of what you've seen happen?
Yep. And so this goes back to the need to actually include the commercial sector, the private sector in these conversations. There is some really interesting things happening in the different states. I wrote down the ones I could think of. Texas Space Commission, Australia Space Institute, Ohio State, the George Washington Carver Science Park, all of these different conglomerations of universities and private sector that are working together for space, for commercial space and the space economy. I think that's the starting point. And like making sure that in those conversations, supporting them and all of the things they're doing, but in those conversations, making them understand that biodefense is an issue. And anything where humans are, we need to start thinking about what does that mean for their health in space, for the health back on Earth, for planetary protection, forward and backward contamination.
And Dr. Limerick, before you also answer that same question, HR 6131, even though they had hearings in the House, was it Energy and Commerce or Science Committee? Do you know which one?
It was science.
Science?
Yeah.
So it didn't get enacted. So has it been reintroduced in this Congress?
Not that I know of, but given the progression, I would assume that it's more likely to be introduced. That bill is more likely to be introduced than the proposed legislation from the Biden White House. So that's the one that I focused on.
Okay. Perhaps we can help you with some recommendations on that. So appreciate your words on that. But tell me again how the federal funds cutback that are clearly coming, how that impacts your specifics.
So I'm talking policy here with respect to this talk today, but looking more broadly, the most immediate is the president's proposed budget summary indicates that the Mars sample return mission will be canceled. The Mars sample return mission is the foundation for all of the new work that we're doing in planetary protection within NASA. So all of the innovation that goes into coming up with the methodologies for dealing with a restricted Earth return of sample materials from another celestial body is all stopped as a result of that. It should be noted that Nick talked to the concept of both unrestricted Earth return from like an asteroid and restricted Earth return as for Mars. We've conducted internationally and within the United States, we've conducted numerous unrestricted Earth returns. So there's a backlog there's a history of practice there. We have not conducted a restricted Earth return either internationally or within the United States. The Mars sample return would be the first. Cutting off the funding for that cuts off all of the innovation in planetary protection.
I think we're going to get into that a little bit on our last panel. And Dr. Rick Majors, my brother-in-law served in the Air Force, a pilot. He actually flew the missions virtually every week into Antarctica from New Zealand.
Oh,
I don't know if maybe you were on one of those flights at one point, but I think you're too young to. He's now retired. But you're funding much of it NSF funds, or tell me how things stand.
Yeah. Yes, so the Antarctic Research Program is reliant on the National Science Foundation and on contracts that go through the National Science Foundation. So certainly the current funding situation presents a big challenge. And I would say even outside of the Antarctic, you know, I tried to focus my remarks from kind of a basic science perspective, because I do think that those types of questions are really critical when we're moving into areas that are unknown, which is what we're talking about here, right? It's exploration. And in order to effectively explore, you need to have a basic science framework to work from. And so the current funding uncertainties, I think, they leave a lot of questions for what's going to happen to basic research in this country.
Well, thank you, Dr. Shalala.
Just a quick question for Dr. Lindberg. If I remember correctly, you were a member of the National Academy of Sciences Committee on.
I currently serve on the Committee
Yeah.
for Planetary Protection.
Were any of those recommendations adapted by NASA? Because NASA commissioned the report, if I remember correctly.
So we've generated 3 reports. The report from 2018 was before our committee.
Right.
That was a different ad hoc committee. Our committees generated 3 reports: one on the moon, one on small planetary bodies, and the third on Mars. And NASA's embraced the recommendations of our reports in all 3. And in fact, our recommendations on planetary protection for the moon were adopted by COSPAR as well. So they were adopted internationally. COSPAR depends on reports from, leans heavily on.
Summarize some of
National
those
Academy.
recommendations.
Thinking back, the recommendations on the moon were that the moon could be treated as an unrestricted Earth return, and that the protection of materials at the lunar poles that are trapped in the craters that are permanently shadowed at the lunar poles should be protected by keeping a log of both biological materials and organics that are taken to the moon on missions that land on the moon.
And on Mars?
I'm trying to remember what the Mars, I have to go back and look.
Okay,
Thank
that's fine. That's fine. I just wanted to point out that you had played a role in the National Academy's own review on these issues.
Yes.
Senator Daschle.
Well, thank all 3 of you for just an excellent presentation. I'm just curious structurally. I think as we look to the future, it's highly likely that the integration of public and private sector work and projects will become even more apparent. And I'm just curious if you could just share with us your insights based on your experience. How can we make the public-private partnerships in this area more successful? What can we do to ensure that that integration is as good as it can be, given the complexity, the uncertainty, and the costs involved? Maybe could we just go down the way?
Sure. Yes, I agree that public-private partnerships are really critical in this area. As I mentioned before, I think academia has a great strength in basic research, but also in applied research. And so I think that in order to move forward in this space, we need to create infrastructure that produces better communication between these sectors. Sometimes we end up speaking different languages. We function often under very different timelines and different regulatory structures. And I think that those things can be a challenge. We can learn from each other, but it also makes it a challenge to make progress. And so I think working towards building communication that helps with understanding across those boundaries is really critical.
Can I just clarify?
Yeah.
It sounds as if what you're telling us is that today communication isn't what it should be, and that we really need to work to put greater emphasis on better communication both ways.
Yes, I think, I mean, I can't speak for all cases, of course. I'm sure that there are cases where there's excellent communication. But I don't think that it comes naturally to all collaborations. And I think there are programs, I'll mention DARPA that Anne has worked with. I'm also a DARPA researcher, and I think that DARPA does a really great job of helping academics build these types of frameworks in which we can really move forward in ways that are relevant to technology. And so I think supporting programs like that is a great example of something that can work.
Thank you. Dr. Lindberg?
I'm going to take a completely different angle on this one, but thank you for the question. In 2 words, regulatory certainty. The challenge that emerging space companies have is not knowing what regulations they have to comply with. So regulatory certainty, and to a lesser extent, the sharing of best practices from NASA and other agencies that can benefit, and the sharing of technologies that can benefit private sector engagements. But NASA's typically willing to do that. They do a good job of that. And in planetary protection in particular, Dr. Benedini leans forward in looking for opportunities to take the very obtuse art of planetary protection and share it with the broader space community. But I think regulatory certainty is a critical need.
Very helpful. Dr. Cheever?
Yes, thank you. So Trista is referring to ice crystallization control for extreme environments, one of my other programs at DARPA. I don't have favorite programs, but that was up there. So no, the role of a funder at DARPA, a role I took very seriously, was one of integration of our academic teams and our commercial teams, and facilitating that very communication that you were talking about. But we did it with money behind it, like they had to. Like, you want to be part of this program, you must share this data, or you must overcome these IP concerns. We can figure it out. We need to work together for this ultimate program vision. And if you don't, we'll cut you. So, I mean, so that's like, that's a very like clear cut case. I know that it's not always that straightforward. So there's a couple other things that come to mind. The role of public-private partnerships, so in the role of government, it's interesting. And in some ways, I think that role of government to facilitate the private sector and commercial companies is as sort of the holder and facilitator and convener of data. And so there's a way, I think, and there should be a way that government can play a role to have a source of data, layers and upon layers if needed, classified all the way up to, IP protected or anywhere in between, where researchers can come and access that data. And so, and it's not trivial, right? I know that's not an easy undertaking, and it does take resources, but I think that is a very crucial role that the government should take in this for public-private partnerships. And then the last is, these commercial LEO destinations, these private, there's 5 of them in the running: Axiom, Orbital Reef, Starlab, Northrop Grumman, and Haven by VAST. These are in various, stages of readiness. I'm going to take the very unpopular stance and say that government should weigh in and pick a winner or 2 and just, push them up. And maybe these conversations are ongoing and I'm not aware of them, but I really think in order to stay in the lead in terms of US leadership, especially with near-peer adversaries that are very interested in LEO and the lunar surface, I think we just need to hurry up.
Very helpful. Thank you.
Jim Greenwood.
Thank you. So Dr. Vic Majors, the sub-glacier microbes that you discovered, and I know you were very careful about making sure that they didn't escape, but were you able to bring them up and then experiment on them to see how they survived under various temperatures?
Yes, we were actually. So we brought up samples of both water and lake sediments from those environments and did a number of experiments on them, ranging from characterizing their genetic information to incubating them in the lab and testing how they respond to temperature, actually. We did not take them down to, say, very, very low temperatures like you might find on Mars. We were interested in knowing whether they needed the low temperatures that are present in the subglacial environment in order to survive. And we found that they like those temperatures, but they actually do quite well at more Earth surface relevant temperatures that are comfortable for us.
So as a model, if you're thinking about the possibility of microbes on Mars that live in very cold, and then whether they could survive, you found that these microbes at least could survive in.
Yes, exactly. They have
Temperatures above zero.
surprisingly broad ranges of tolerability for different conditions.
Thank you.
Yeah.
Dr. Lindberg, on the fact that the regulatory agency has not been created, can you talk about what with the resistance to that? Was it just, was there political resistance to it, and did it have to do with creating a new agency? And could that regulatory function be done in an existing agency so as not to, the environment is not good for creating new agencies right now?
Oh, no, we have to name I shouldn't suggest that we need a new agency. We certainly, both the White House proposal from the last administration and the congressional bill from the last Congress contemplated giving part of that role to Commerce, part of that role to the FAA. I didn't, or Department of Transportation. I didn't want to come forward with a recommendation that any particular agency was the right one, but rather that a regulatory agency, not NASA, because they're not a regulatory agency, needs to be the point agency for this, and it inevitably will require coordination, and the approval of return samples on a restricted Earth return is going to require White House participation and White House leadership.
Was there objection to the bill, to that language, or was it just that Congress didn't get to it?
No, I didn't have an objection to selecting Commerce.
No, that's my question is the Congress didn't pass this legislation.
That's true.
And my question is that because there was opposition within the Congress to it, or was they just didn't get around to it?
No, they didn't get around to it.
Okay.
I think it would have moved forward. I'm hoping that it would have evolved as it moved forward, but it was reported out of committee and then stalled.
Okay, thank you. And for Dr. Cheever, you talked about microbes manufacturing things in space, and you referenced, I think, tissue engineering, cell engineering or cell therapies, probably genetic therapies. Are you thinking that that's going to be mostly sort of in the regenerative medicine, life sciences side, or do you envision these microbes manufacturing non-living organisms or working with non-living elements?
Yeah, absolutely. So there, I bifurcated in my mind to pharma and non-pharma products. And so from the bioindustrial side, you have the pharma side for therapeutics or drug discovery or sort of that side of the human health equation in terms of a product that you could produce in low Earth orbit versus a bioindustrial side. And for me, that really kind of means sort of human habitation and sustainment in that environment. So I'm talking about biomanufacturing to produce things that you need in space, so you can make it there and not have to take it. And so
making things like plastics, or for instance.
Yeah, absolutely. And as part of the Be Sure program, we did not dictate what they wanted to make in space, but we said it just had to be DoD relevant. And that's a pretty big list. So they made things from beta carotene, and that could be used as a nutrient. So you are on the food side here. They made PLA, that's a 3D printing precursor, polylactic acid. So it's a very low temp precursor to put into a 3D printing machine. But that's just the starting point. there is a program called Living Foundries. I was the last program manager at DARPA, and we made over 1,600 molecules using microbes in fermentation. So the list of what you can make on the bioindustrial side, specifically with microbes and biomanufacturing, is very large. Now that does take optimization and scale up, and especially for space, it's going to take hardware and bioreactors. But there is a very the whole goal of the BSHO program was to answer the question, is biomanufacturing a viable manufacturing paradigm for space? That was the whole point. Show us with microbes and with the data and with an actual biological approach, can you use this? And the answer was yes. The next step is to now actually create the hardware and validate it and test it in the space environment.
And does a lack of gravity create new opportunities for manufacturing?
For biomanufacturing specifically, we did see increase in production of certain molecules in microgravity. So we tested all the different gravity levels on the ISS. So we had 3 launches. Shout out to our wonderful payload integrators, Rhodium Scientific. We got 3 payloads up to the ISS to validate the different gravity levels. So they used a centrifuge to simulate Mars gravity, lunar gravity, and Earth gravity on the ISS, and of course microgravity on the station. And so there were interesting results from our University of Florida team showing that some of the gravity levels actually increased production. And so there's just an enormous amount of R&D and testing that needs to go into this to understand what the potential is there. But it's definitely that data is starting to come out and published. Yeah.
Thanks much.
Susan?
You mentioned, Dr. Cheever, that ice crystallization was one of your, was one of the top projects you were focused on at DARPA or followed. What were your top 1 or 2 ice crystallization?
Yeah, I mean, I only say that because they were my programs and I developed and pitched them. But but ice was certainly up there. Be sure, ice, and then I had a classified program. But those were my favorites. I had a total of 7 programs, and so I don't want to play favorites of those programs I also inherited. But my portfolio ranged from genome engineering, biomanufacturing, material science for the ice program, all the way to some soil mitigation using microbes. So it was a very broad biotech, operational biotech focused portfolio.
You mentioned in your opening comments, the National Security Council and your work there. Can you just share with us, how do these topics that we're talking about get before the National Security Council?
Yes. So that's something that I would love to figure out a remedy for, because the role of a director on the National Security Council is a very busy one, but it's a role that can really convene the interagency around a topic. And so I want to find a way to actually promote that intersection of biotech and the things that we've been talking about in terms of astrobiodefense, even just biodefense and biotech innovation on the National Security Council, because of that convening power and that ability to promote and write policy and bring together the interagency to talk about it. And ultimately, it's a bottom-up policy approach. It can be top-down in executive order, can be bottom-up as well. And so I think, the right person and the right sort of ability to kind of do that would be really interesting. Traditionally, and in the last administration, we were kind of split between technology and national security, which was very much a US competitive PRC. How do we, implement expert controls to protect our innovations? And then we had HSB, so Health Sec Bio. So they were focused on biothreats and pandemic preparedness, lived at OPPR. And so we worked together often, but it was constructed in such a way that those cross-cutting topics were very difficult to kind of bring together. I'm still kind of thinking through how to best approach that, but OSTP's role in their ability to convene as well is super important. But it is very different in terms of policy and actually enacting input and promoting a policy process.
Thank you. That's all.
Ken?
Okay, thanks. Dr. Lindberg, I'd like to follow up on Jim Greenwood's questions about the regulatory space as it applies to commercial ventures. Interesting, you mentioned earlier the desire for regulatory certainty. And when Representative Greenwood was asking you about the legislation that was proposed last time, sounds like it just sort of died on the vine, ran out of time. But in terms of opposition to it, was there stiff opposition to it from industry? You mentioned in your remarks something about, freedom of space travel or whatever. Or was there actually a hunger for some kind of regulation on the part of the industry because they want that certainty that you cited?
There was a hunger on the part of industry for that regulatory certainty and for the bill. I think the opposition to it came actually from the White House, in that the White House saw a different path to doing a different implementation of that regulatory process. I think the House bill was flawed in that it tried to steer too hard toward the interests of industry not to be regulated, rather than the interest of the United States to comply with treaty obligations and assure proper surveillance of non-state actors. That's my opinion.
Okay, so and this is a tough question to answer, but just in broad strokes, setting aside what was in each of the proposed bills, setting aside what the treaty obligations might be or might not be, what would you recommend as sort of the broad strokes of regulatory regime that would govern commercial space travel and protect against the bio threat, either going external or coming internal?
So number one, I'll talk within the context of planetary protection, which is a small piece of the overall regulatory requirements for commercial space.
Right.
For planetary protection, consistency with NASA's policy and COSPAR policy, which are well aligned, I think is the foundational element, that private actors should be held to the same standard that all spacefaring nations are held to today. The second piece of it is the need for an interagency review for returned materials, that it can't be done by a single agency within the United States. It can't be done by NASA alone. Even for NASA missions, it needs to involve the Environmental Protection Agency, the National Institutes of Health, the CDC, the Department of Agriculture. You can go on and on. You can see all the roles that would be involved in assessing the bio risks of a return from Mars, of either returned materials, like in Mars sample return, or the return of humans eventually from Mars.
Would you recommend there be a licensing regime of some kind, that you have to get a license before you undertake?
Yes.
So, and that license would be based on showing what the protocols are that you're going to follow to ensure biosecurity?
And that you submit to continuous monitoring, which is part of it. Yeah.
Okay, thank you.
Asha.
Thanks. Just quickly. So we've heard in the skinny budget that came out that there is a possibility of cutting the Mars sample return mission. Do you think it is even possible for us to think about going to Mars without having the Mars samples come back and be examined first? All of you.
Yeah, okay. I think it complicates that endeavor immensely, and in ways that I'm not sure we can even measure. If we are talking about sending humans on missions to Mars, there's the science part of my brain that says we need to know if there's life on Mars, or if there's evidence of past life on Mars, and doing something that could limit our ability to understand that is really, really damaging. So that's the science side of my brain. The practical, more biodefense focused side of my brain says that there's a huge risk in doing that. We go there and we don't have any idea what is there. then it makes it very hard to prepare for what we're going to bring back or for what humans might encounter while they're there.
Can I just quickly sort of follow-up question very quickly? So you go sample Mars, it's a big place. How do you find nothing in the samples, but that doesn't mean that a mile away there could be. So how do you deal with that?
Yeah, I think that's a great question. And it's a huge challenge as well. I think that, thinking in terms of what we need to know versus what sort of investments are reasonable, I think it's really important. And I think, people from NASA are the ones that have the expertise to make those decisions, but making sure that we're targeting locations that are going to be the most informative when we're doing sample return.
or something.
Yes, yeah, exactly.
So to your point, we've been thinking about going to Mars and bringing things back for quite some time, and that's evidenced by the fact that that well before my time helping the National Academies, there was a report, I think in 2005, but I could be wrong, called Safe on Mars. And that report called for the characterization of the landing site for a human mission to Mars before the human mission is undertaken. And that characterization would include the potential for both the possibility of extant or extinct life at that location in particular, and also the characteristics of that location as it points to the possible support of replication of Earth life that we might leave there. It's well understood within the science, within the space community, that when we take humans to Mars, we can't possibly not contaminate Mars. Dr. Polk talked about the human biome. Well, the human biome gets into the atmosphere, and the atmosphere will be exchanged between the habitat and the Martian atmosphere. And so the human biome will find its way into the Martian environment. The question is, can those microbes replicate on Mars, or are the biocidal factors such that they can't possibly replicate and spread? That has to be characterized before we take humans there.
Completely agree with everything was just said. I would only add that I think it is really important to have that sample return, because I would love to know and characterize what's in that regolith, because there is a manufacturing reason. I mean, for human habitation, or you're going to be there any length of time, you kind of need to know what's in that regolith for human sustainment or in situ resource utilization, or especially biomanufacturing. Part of the program was to understand what we can pull out of lunar regolith in order to support a fermentation system for production and manufacturing. And so actually validating that from Martian regolith would be actually really important.
Well, not that you guys asked my opinion, but I would say that, this is not the 1600s. We're not launching across oceans and wondering if we need to have an America sample return program, right? I mean, we're going across the galaxy. We have the ability to do it. Just feels from like a recon perspective and a data perspective, we should do it. But that's my opinion. Just quickly, and do you think that NASA itself is sufficient in terms of advanced research projects, or do you think that NASA needs like a DARPA arm, a NARPA, if you will?
Yeah, a NARPA? I don't know. Sorry. So I've often struggled with this, so I'll try not to go too long on this. NASA has an enormous wealth of expertise and knowledge, but they're not a national security agency. And for me, this topic is national security and economic security, which, same thing, right? Economic security is national security. So I think that they need to be part of any conversation in any endeavor, but I don't think that their mission is national security, and I think that's at odds with what we're talking about.
Okay. Trista, when it comes to the research we've done in the Antarctic, it makes perfect sense. We're going after and looking at extremophiles and just trying that this is what we have access to, and it's worth. But at the same time, there are going to be challenges scientifically for applying what we've learned about that directly to some other planet. How do you think we can overcome that challenge, or are we just stuck saying this is what we got, this is what we understand, and we have to go over there and just start comparing and contrasting?
Yeah, that's a great question. And it's a really big question. I think, I mean, there is some amount of you don't know until you go there and you try. But part of what I was thinking about when I was preparing my remarks was that, we have these opportunities on Earth to study microbes that we can see, to make inferences based off of what we know. And that's an important thing to do. And we should keep doing that and keep interrogating that. At the same time, as you pointed out, it doesn't give us all of the information that we need. And I think that we can start to use more of the computational tools that are becoming more readily available to come up with creative ways to understand life and look at its possibilities. So kind of move out of the space of this is what we already know. Could it work over here? To saying, well, this is what we know. This is kind of adjacent to what we know. And does that get us closer to something that's relevant to Mars?
Okay.
Yeah.
Great. And Bob, we've talked a lot about regulatory authority and lack of regulatory authority. Do you think we should just add regulatory authority to NASA?
That would not be my, I think that would
Everybody
add a
can
whole,
see your face in the back here.
that would add a whole layer of structure to NASA that I think can already be found in other agencies. So I don't think it's the most efficient way to
Okay.
deal with it. I think NASA brings the technical expertise, and that process works well with the current FAA process for launch licensing. I think we turn to a regulatory agency.
Okay. Great. That's it, sir.
Well, thank you all. That concludes our panel. I think we're going to forego the break that we had just to keep rolling, if that's okay. So thank you for your help today, and good luck in the future for sure, all three of you. Thank you.
Okay, our next panel, our fourth and final panel, is about how science and technology innovations for space and planetary protection can be applied to improve biodefense capabilities on Earth. And I'd like to invite our panelists to come forward, please. Okay, welcome. We have as our panelists, if I may just briefly introduce them, and you can please elaborate on your own bio. Former NASA Planetary Protection Officer, Dr. Cassie Conley. We have Michael Meyer, who is former lead scientist for Mars Exploration Program, the National Aeronautics and Space Administration. And we have Dr. Christopher Carr, who's assistant professor at the Daniel Guggenheim School of Aerospace Engineering and the School of Earth and Atmospheric Sciences, the Georgia Institute of Technology, research fellow at the Massachusetts General Hospital in molecular biology, and otherwise you're just goofing off, right? Just kidding. Have quite a portfolio. And why don't we start with Dr. Meyer?
Members of the committee, I thank you for this opportunity to speak to you today on the history and future of Mars exploration by NASA and the implications for science, technology, and biosafety in civil and commercial space exploration in the future. As in my background, as mentioned, I was the lead scientist for the Mars Exploration Program. I was also the lead scientist for Mars Sample Return. Been the program scientist at a couple of missions to Mars. I was the senior scientist for astrobiology and also a couple of years planetary protection officer. So, and this is a nice marriage of my diverse career. And I started as a researcher of life in extreme environments. So the exploration of Mars, even before the existence of NASA, has been inexorably tied to the search for life, and Mars exploration at NASA has been operating for nearly 6 decades to understand more about our nearest habitable neighbor. Over the past 3 decades of Mars exploration, our missions have transformed how we understand the red planet and whether it has or ever has had life. The Spirit and Opportunity rovers demonstrated that Mars once had a warmer and wetter past. The 2001 Mars Odyssey orbiter revealed large subsurface water ice under the poles or near the poles. Curiosity rovers demonstrated that the surface of Mars was once habitable. And together with MAVEN, the MAVEN orbiter, have provided clues to loss of water from the Martian atmosphere that gives us the environment that we have today. And finally, the Perseverance rover, collecting samples on Mars today, is searching for signs of past life. Both of our operational rovers have made some tantalizing discoveries of organic material. In the planned return of these samples collected by Perseverance and the Mars Sample Return campaign, one of the questions would be tied to how the approach of backward planetary protection, the control of materials returned from habitable worlds elsewhere in order to prevent potentially harmful consequences to humans and Earth's biosphere. So I want to emphasize, it's not just whether or not it's a problem for humans, it's also a problem for our Earth environment. It could be kudzu or something like that. The current approach to back planetary protection on Mars sample return will be transformed simply from the sterilization of uncontained Martian particles and return of flight to the prevention of uncontained material by breaking the chain of contact between Mars and Earth and doing it at Mars. The updated approach moves Mars sample returns back planetary protection from the realm of biology to a more predictable world of controlling physical movement of dust particles by mechanical means. The updated approach is based on principles of isolation and purposeful handling of the sample tubes that reduce the potential hazard at every successive step. It significantly increases the simplicity of careful back planetary protection approach necessary for Mars sample return while increasing the specificity of the mathematical calculations required to show that Mars sample return can be done safely. Once these samples to the Mars sample receiving facility, where they will come, the critical part of Mars sample return, it will need to undertake further assessment of the sample safety, and researchers at the sample receiving facility will conduct under strict containment, preliminary examination and analysis of unsterilized samples collected and returned to Earth. The facility will be required to implement planetary protection category 5 restricted Earth return requirements and contamination control requirements. Recently, the Sample Safety Assessment Protocol team has completed work to extend the previously outlined sample safety assessment framework into a proposed protocol. The protocol would involve these major sequential steps that include Bayesian statistics-informed decision-making, using a small fraction of return samples and measurements that could be used both for science and backward planetary protection. The development of the protocol would be a long-term benefit for assessing the likelihood of Martian life as we prepare for future exploration, both civil and commercial. Furthermore, the developments and lessons learned would provide a wealth of practical knowledge in handling novel hazardous material from other environments. Additionally, the robotic planetary missions, we are beginning in earnest life detection investigations, including understanding microbial survivability in Martian environments, and contamination control in these planetary missions is becoming even more critical to enable a very precise and difficult astrobiology measurements that are susceptible to contamination. As we consider exploration even further into the future with humans rather than robotic explorers, planetary protection will be both critical, both for maintaining the integrity of scientific investigations by the astronauts that seek to determine if life existed or existed on Mars, to protect the crew from any harmful indigenous Martian life forms, and to protect the terrestrial biosphere from potentially harmful release of Martian life on Earth. Mars exploration in the Science Mission Directorate has had a continuous experience in trying to identify the potential life for Mars through exploration, laboratory research, and the study of analog environments on Earth. There's three recommendations that I would like to put forward to this committee. One is continued funding for research and exploration. Funding is the key to enabling us to further our understanding of the Martian environment, resulting in safer human exploration in the future. The past decades have shown that while we can understand the Martian environment by comparison to our own, there are many significant ways that they differ, and continued research and exploration are a key to understanding these differences. This includes research into life as we don't know it, the unknown unknowns about identifying life elsewhere. Number two would be the continued workshops with the goal of formalizing the presidential directive NSC 25 to include back planetary protection. The current language of the presidential directive is somewhat vague on the process for obtaining a presidential decision on an experiment that may impact the environment that does not mention backward planetary protection. It would be beneficial to continue engaging in workshops that include commercial partners to assess the interplay between planetary protection and human exploration. And third, conduct Mars sample return mission, establishing back planetary protection protocols for human missions to Mars poses a challenge that can be better informed and potentially mitigated to a significant degree by robotic return of scientifically selected samples, presenting the potential for enormous savings in time and resources. Completing Mars sample return, therefore, provides benefits not just in science, technological innovation, and leadership in space, but potential cost savings in the human future exploration of Mars. There are three approaches that one could envision for back planet protection on human spaceflight to Mars. The first would be to develop protocols on precursor robotic missions returned that would inform and potentially mitigate human back planetary protection protocols by developing new technologies, new processes, and defining methods of meeting regulatory regimes while also providing new data on the Mars environment. Second approach would be to determine the human spaceflight protocols without robotic precursors, requiring significant higher investment in technology mitigation and wider engineering margins. And the third approach would be to ignore back planetary protection altogether, placing the U.S. at odds with its obligations under the Outer Space Treaty, likely leading to other nations ignoring provisions of the treaty to the detriment of our U.S. interests. And thank you so much for your time.
Okay, and thank you, sir. Dr. Carr.
Thank you, Governor Ridge, who I think is no longer with us at the moment, but thank you. Secretary Shalala, commissioners, the executive director, panelists, and everyone in attendance today. We are all here to make common cause in advancing astrobiodefense and promoting health and security in the United States. Today, I'll be speaking in my personal capacity. Imagine a bioactive molecule is returned from another world. To cause appreciable harm, it must reach Earth, escape containment, and cause a negative effect in a host or the environment in a way that amplifies exponentially. We're discussing how to address such threats with science and technology, yet we're currently failing to address known threats, such as measles, with safe and effective solutions, vaccines. Instead, we are bearing witness to the dismantling of the engine of fundamental research, which drives long-run health, wealth, and prosperity of our nation. The undermining of evidence-based practices and the broad-based cuts underway, as we've heard earlier, will not only cede areas of national competitiveness to other nations, but also actively undermine our shared interests. Correcting this trajectory is a precondition to any rational astrobiodefense strategy. Looking for life beyond Earth is a bit like trying to find the keys you dropped in a parking lot at night. The story goes, don't look under the lamppost just because it is lit up. But if you think you dropped your keys there, it's actually a great place to look. We now know that the universe is a carbon chemistry factory. The building blocks of life as we know it are made in space, as well as on and in planets. To find our keys, we may need to search in the dark, but we should probably also search in the light. The building blocks of life beyond Earth might not be that different. A leading theory of the origin of life, the so-called cyanosulfidic model, could have occurred on early Earth or early Mars. And early Mars might be a better fit. If life evolved there first, it could have been transferred via large meteorite impacts that produced 1 billion tons of ejecta reaching Earth without being sterilized. Thus, life as we know it may have started on Mars and been transferred to Earth. This hypothesis sounds maybe wild, but can be confirmed or rejected through sample return and future Mars missions. If true, and there is still life on Mars today, it may be able to interact with biology. We might also leverage tens of billions of dollars of public and private research and development to detect it. My first recommendation is to advocate for NASA to include the capability to detect and characterize life as we know it as part of return sample analyses and future life detection missions. This could help to detect forward contamination, thereby avoiding false positives, as well as detecting indigenous life with similar building blocks, and that could result in actionable information for planetary protection and biodefense. Astrobiology can also help us think beyond life as we know it. Molecules have a handedness or chirality. We don't know why life as we know it uses left-handed amino acids or right-handed DNA molecules. If Mars life originated in a similar way, but uses different handedness, it could have some of the properties hypothesized in the recent report warning against creating mirror image life. And such mirror image life could be missed by current technologies, such as DNA sequencing. Different environments also help us broaden our thinking. Biology uses water as a solvent. The upcoming Dragonfly mission will help us to better understand what organic chemistry is possible in liquid methane on Saturn's largest moon, Titan. Recent work suggests that chemical complexity is also possible in concentrated sulfuric acid, which dominates the clouds of Venus. These and other diverse environments can be studied through lab experiments or via exploration, such as we will do as part of our upcoming Rocket Lab mission to Venus, a unique partnership. But increasingly, there is another option, computational study using quantum chemistry. My second recommendation is to apply machine learning accelerated quantum chemistry tools to assess, bound, and mitigate astrobiodefense threats, such as the threat of small bioactive molecules to induce prion-like infection or the potential harms of mirror image life. We can use this and other methods to refine the appropriate critical particle size for Mars sample return or other return sample scenarios. We also must use new methods to detect and characterize single molecules that are simultaneously broad and simple. Let's say we sampled aerosols in this room and wanted to detect the presence of an unknown virus. For viruses, this heritable material can be DNA or RNA, two possibilities. It can also be single or double-stranded, like the classic double helix, two more combinations. Now consider mirror image life. Current sequencing methods use enzymatic and chemical steps that would be different in every case, requiring 8 different protocols. Do this by hand and it would require an expert. Automation would require a very complicated machine and test kits. However, using a nascent technology called nanogap, it may be possible to have only a single protocol. Instead of using biology to facilitate detection, this technology electrically reads the conductance of single molecules or parts of molecules and avoids many of the sample processing steps. This is but one technology under development that one day could be applied to biodefense. Future NASA missions demand more versatile and robust methods of sample handling, which is also a barrier for high throughput requirements of envisioned biodefense monitoring systems. My third recommendation is to advocate for federal, such as joint NASA or NIH, funding to translate life detection technologies into biodefense applications, especially co-funding robust sample handling automation. One simple example to identify candidate technology: NASA's instrumentation programs, such as Picasso or Matisse, could incorporate a checkbox and short description of self-identified relevance during proposal submission. I've made the case that life beyond Earth could share similar building blocks to life as we know it, and that for Mars could share a common ancestor. Thus, seeking life as we know it should be part of return sample analysis in future missions and can inform the risks of adverse interactions. Second, quantum chemistry and other computational tools can facilitate assessment of risks posed by bioactive molecules and mirror image life and can help clarify mission requirements around the probability of release of unsterilized extraterrestrial particles. Third, I've given an example of how NASA-supported instrumentation may simplify and broaden detectability of biodefense threats and how joint efforts are needed, especially around automation of sample handling. Such joint efforts can also leverage public-private partnerships, which have been instrumental in several relevant areas, including advancing nanopore sequencing, as well as facilitating our upcoming mission to Venus. I leave you with this message. Fundamental research is an essential pillar of biodefense. It has brought this country over a century of advances in public health and will pay dividends well beyond. We cannot prevent what we cannot envision. Thank you.
Thank you. And Dr. Connolly.
Thank you. This seems to be on. Yes, I am one of 3 planetary protection officers that you have heard today. I think I have the unique qualification of having contaminated the Earth with animals, because before I started as planetary protection officer, I had an experiment on the Columbia shuttle crash that allowed my nematode worms to survive the crash. So I was in the unique position of saying, do what I was saying and not what I had done. That being said, I would like to make my general recommendation being to use some of the lessons of past activities to inform what we do in the future. This commission, thank you very much for having me, is probably the first time that planetary protection has received this kind of attention since the Apollo program. It did receive this kind of attention during the Apollo program. PDNSC 25, that has been mentioned, was created, the precursor to that was created to support the Apollo sample return mission of humans and Mars lunar materials. That is actually the first time that any country on Earth had tried to do a restricted, what now we call restricted Earth return mission. It was at the time considered only a sample return mission. And it was wonderful to hear all the NASA representatives saying all the right things. However, it's important to look at the details because that's where the problems are. If things are not implemented correctly in practice, it becomes a problem. Everybody may remember who was aware of the Apollo program, the astronauts suits being tossed into the capsule, the astronauts put them on, they come out of the capsule, they get into little boats, they get helicoptered up, and then they walk into the quarantine facility. That was done because of budget cuts that did not allow the entire capsule to be lifted onto the ship where the quarantine facility was located so that the astronauts could go directly from the capsule into the quarantine facility. Budget cuts are a problem. In addition, the level of coordination at the all government level definitely needs to be increased. And I'm very glad that the commission has already recommended the formation of an interdepartmental advisory committee. In 2006, when I started as planetary protection officer, I inherited an advisory committee that included representatives from the CDC, from the USDA, from the Environmental Protection Agency, from the DOD, from the FAA, as well as scientific experts in areas of planetary science, biology, communications, various other different social concerns. And that advisory committee spent a lot of effort with me working on trying to ensure coordination between NASA and the FAA. Just before I left the planetary protection officer position in 2017, I had been involved in the FAA approval of the launch of the Tesla car that was supposed to be launched on an orbit sort of vaguely in the direction of the asteroid belt. In fact, that Tesla launch was sent in a direction that intersected the orbit of Mars, not too long off from where Mars was going to be there. And yet which was not the approved launch trajectory. So the FAA approved something that the company SpaceX actually did not do. They did something different. But because there was no capability of changing the trajectory of the car after it had been launched, there was no way for the FAA to direct SpaceX to make any changes. And to my knowledge, there was no consequences whatsoever for SpaceX about the fact that they had submitted and gotten launch licensing from the FAA for a trajectory that they did not actually use. So ensuring that the regulatory oversight is actually effective is a very important element that needs to be done. The Apollo program, of course, has been cited here as a representative that we want to aspire to. But the back contamination committee actually faced similar challenges in that the quarantine facility was intended to contain lunar samples in a way that they were not contaminating the Earth, and the samples themselves did not get contaminated. The original way to do that was to pull a back pressure on the containment chambers that were at Johnson Space Center. They breached. And so then immediately people were worried about, oh, the samples are going to get contaminated. So they put overpressure into the lunar samples that was, again, blowing potentially lunar dust out into the Earth environment. This was not optimal in terms of protecting the Earth. Of course, the moon was not expected to contain life. So, and the moon and the Earth exchange material fairly often every time there's a meteorite impact. So that a large meteorite impact. So that wasn't actually a major problem for us being protected. But the question of whether what would have happened to the astronauts, and the astronaut on Apollo 13 did get sick, but that was prior to any contact with lunar materials. If an astronaut had gotten sick on the way back from the Apollo program, was there any opinion about what would have been done? There was a concern about the Apollo program's landing and not coming back. And there was, of course, the famous speech that never got made about how the Apollo program failed. Most robotic missions have failed. If we send human missions to Earth, it's not unlikely. Past evidence suggests that the first human missions could fail also. We got lucky on the Apollo program. And then if the human is getting sick on the way back from Mars, we've heard about the quarantine over the 6-month return. But if somebody is sick and we don't know what they're sick of, should that capsule be allowed to land? I don't know that there has been any thought about what we actually do in some of these worst case or bad case scenarios. And of course, the reason we're doing all of this is because humans have always explored. When you start out, you walk across to the next valley to understand what's there. We found other humans. We go across the Atlantic from Europe to the New World. We found other humans. We found all kinds of other things. Columbus took his sailors back to Europe, and they brought something that turned into syphilis with them. The consequences of syphilis to the politics of the European continent were enormous because all of the upper classes were sleeping around with each other. And that then caused entire ruling families to disappear. So the consequences to the explorers, not to mention all the consequences of the people who were less politically and technologically powerful, are not always good. And in fact, very often are bad. So that is another thing that we should be thinking about. Planetary protection was actually proposed by the International Astronautical Federation in the 1950s, before the launch of Sputnik, with the goal of saying, let's learn from what we have done already and do better in the future at a global level. I think that was probably the only, or at least the first time that humans as a global society actually took precautions to avoid something that we knew we had done in the past and we didn't want to do again. Carl Sagan, early on, was a graduate student very early during those discussions, and he pointed out the challenge that we face with exploring somewhere like Mars. There is life on Mars. Our spacecraft have put it there. Not all the spacecraft that went to Mars were perfectly sterile. So there is already Earth life on Mars. If Mars life is related to Earth life, that makes it much more difficult to tell the difference. If Mars life is distinct from Earth life, it would be like going and trying to find stars in the sky when the sun's out. We know there's one star up there, but we couldn't see the rest. Mm-hmm. So the issue of humans going out in the future, we will bring microbes with us. We have already brought microbes with us to Mars. What kinds of problems they could cause during future human exploration is not something that we spend anywhere close to enough attention being concerned about. So that's my final recommendation, is keep doing the good work to try to ensure that we don't do stupid things because we're interested in exploration. Thanks.
Thank you very much. Perhaps the president will sanction Mr. Musk for changing the trajectory of the Tesla launch.
Oh, we made a mistake in our coefficients.
So, Dr. Carr, if I understand what your basic thesis is, that rather than thinking about applying the technology that we develop in order to go to Mars, et cetera, to biodefense here, we should really develop technologies to better analyze potential bio threats and so forth on planet Earth, and then apply that technology to the space program. Do I have that right?
Well, I think we have to do both of those things. And let me give you a concrete example.
Yeah, that was my
So
next question.
For nanopore sequencing, the current leading technology was developed by Oxford Nanopore. It took about $500 million of private investment. NASA doesn't have that kind of money within its astrobiology program. Wouldn't that be amazing if it did? But it doesn't. And so if we need to leverage that. So one of the things we've been doing is using technologies from the commercial sector and applying that to astrobiology. But we also are thinking in a different way when we're thinking about astrobiology. We're thinking about, could life have different building blocks? Even if it's related to us, maybe there's a different genetic code. Maybe there's nucleic acids, but they have a slightly different or chemically modified structure. So we have to think more broadly. And that can help us expand those technologies or select technologies that are better able to do what's called an untargeted approach of analysis. So we can find things that might be different. So I think we have to leverage the investment that we have here on Earth, and we might be able to do that most appropriately for Mars, but we also can use the thinking, the thought process, and the research in astrobiology that's more focused on diverse possibilities, untargeted assays, and bring that back to biodefense.
Very well, thank you. And Dr. Shalala.
Yeah, if there's competition to get to Mars between SpaceX and NASA, will SpaceX have the same kind of rovers that will collect samples and bring them back so that you can use whatever technology will be available at the time? They're talking about 2026. I think NASA was talking about 2033 or something.
I certainly hope so. One approach there is that if SpaceX is successful in landing a Starship on Mars, that represents a tremendous opportunity for NASA to deploy NASA hardware on a commercial lander. And
I assume these are rovers that will pick up samples, atmospheric samples and soil samples to bring back.
I think that would be an open question. I can't speak to SpaceX's goals for early Mars landings, but I would say that in prior discussions with SpaceX and including participating in some of their they hosted some workshops on the exploration of Mars. Right. They have asked, what should we be doing? And of course, my recommendations include doing science. So I think that is, it's a critically important opportunity, and NASA and others should and probably will have the opportunity to deploy hardware on commercial missions. We might have to accept a very different risk posture than prior NASA missions.
Dr. Meyer, do you think there's a chance of contamination for bringing back samples through the atmosphere?
So a lot of effort has gone into breaking the chain of contact with Mars so that you can get a sample of Mars and bring it back to Earth, have it contained, so then you can study it such that you're not contaminating it, so similar to the concern about the Apollo program, but also that you're not contaminating Earth with the sample itself. It can be done. We've gone through a lot of effort. It's been a huge effort to how to break that chain of contact robotically. It's a big challenge, particularly when you start getting down to, very, very, very small particles. So I think it'd be done. I think it could be done responsibly. I'll point out the obvious. If you're going to have astronauts go to Mars and bring samples back, I can't imagine how do you break the chain of contact when you have an astronaut involved.
So they may contaminate the
well, then they might have stuff with it.
So you really want a rover or something.
Yeah, you want something that you can break the chain. You can not have anything of Mars come back that's not in your sample vessel.
What kind of vials do you use when you're doing?
Well, they look like cigar tubes, but they're titanium.
I think that's the Yeti cups, right? Is that what they are? Just don't break the lid.
Yeah. So, but anyway, I think it can be done, but it is a real challenge, and that has been one of the cost drivers for doing sample return. to figure out how to do this
So we
well and
we really want
verify
a
it.
rover first and then,
And we have samples on Mars now in tubes ready to come back.
yes, right.
So
Yeah, thank you.
Senator Daschle.
Well, thank each of you for your excellent presentations. I'm just curious, given your experiences in research over the years, how much you think artificial intelligence will accelerate your capacity for research and finding answers to many of the questions you're facing today? If you could just elaborate a little bit and give us your insights in that context, I'd appreciate it. Dr.
So,
Conlon?
Artificial intelligence works with data, which means it works with things we already know. When you're coming to something that we don't have any idea about yet, artificial intelligence is only going to be able to hallucinate things based on what we already know. So I would say in appropriate context, artificial intelligence can be extremely powerful, but when it's dealing with things that it doesn't have data about, it's probably worse than the rest of us.
That's a great answer. Every time I ask that question in other contexts, you get this encyclopedia of things that artificial intelligence is possible for further progress. But what you're telling us is that artificial intelligence may not be that helpful.
So I'll give you the example of trying to detect organic compounds on Mars. The Viking project in the 1970s was the cleanest spacecraft that anyone has ever sent to Mars. And that spacecraft had two life detection experiments. One of them was a mass spectrometer that was looking for dead bodies, effectively, organic compounds. The other one was a metabolism experiment looking for reactive materials in the Mars regolith. The labeled release experiment, to the day that PI died, he was publishing papers saying he'd found signs of life on Mars in the 1970s. His data were generally disbelieved because the mass spectrometer found only very small carbon compounds with chlorine attached. And that was interpreted as Earth contamination based on the cleaning fluids that had been used. In 2000, that was in the 1970s. In 2015, the sample analysis at Mars instrument on the Mars Science Laboratory, the investigators using that instrument published a paper saying that, yes, in fact, the Viking mass spec had found indications of Mars organics, which they were able to determine because the rover drove around on Mars and went to different places. And all of the major signals were believed to be Earth contamination, but a few small signals from the SAM instrument were identified as the same things Viking had found in the 1970s that must be real Mars organics because they weren't in all the samples. If we had known in the 1970s that Viking had found signs of Mars organics and found signs of reactive compounds, plus possibly metabolism, we would be in a very different point today. But because people didn't understand what it meant to see, that we're not able to see the Mars material through the Earth contamination. There's so much Earth contamination, even on the cleanest spacecraft, that makes it really, really difficult to understand how to deal with that.
Dr. Meyer, Dr. Carr, any comment?
I'll just add that AI might be helpful in that recognizing patterns that we normally aren't looking for, so we may not recognize. And it's kind of similar to using statistics on metadata, where you can, but lots of data, right? But where something without the bias sees a pattern that you didn't recognize before. And so that could be helpful in that way. It's similar to along the lines of a whole research endeavor started in astrobiology of looking for called agnostic bias signatures. You're not assuming that what you're seeing is a biological signal or a non-biological signal, but you just recognize it as organic. And it's through additional efforts that you can figure out whether or not this is something that's a product of biology or not. So AI can be useful, just like a lot of other tools, but it certainly is not a panacea.
Thank you.
I agree with everything that's said, but I do have some additional context for some applications. So in working on technologies for in situ light detection, we now have missions planned where the instruments we're considering will generate far more data that can be sent back. So that AI, or more broadly machine learning, can help us in situ data processing that will be essential to identify, hey, what is the most important data that we need to send back? And that can also go hand in hand with anomaly detection and recovery, which we can apply at the whole instrument or even at the system level to improve operations. I also want to tell a very brief story. The technology I mentioned, NanoGap, led us to detecting single amino acids, led us to the ability to distinguish life from no life based on organics. Amino acids that are detected in meteorites are not from a living organism, but we can study their quantum chemistry properties and now distinguish that from a set of amino acids that comes from a life-bearing sample. So that's some work that we're just getting submitted. And this leads me to the broader point I was alluding to in my remarks about quantum chemistry. There are now models that have been trained on the entire periodic table, and those allow some predictive capabilities. As was pointed out, we must verify what we're seeing, but they can allow us to do discovery science by giving us a wide range of predictions that we can then validate in the real world. So I think those sorts of models can allow us to see what might be possible, what might occur, and then through experimental or other means, we can validate those and determine, is this bioactive molecule, or is this compound bioactive? Is it likely to cause harm? So we can use that as a tool to we can use AI to refine where we focus our energies.
Well, thank you. Thank you all.
Okay, Congressman Upton.
Well, thank you. I got a couple of questions. So when you talk about the amino acid detection, it sounds incredibly important and valuable. Who actually funded that research to develop the techniques to do it?
Well, the research for the NanoGap instrument is provided by NASA's Picasso program, which funds early stage or low technology readiness level concepts. And so that we're part of that program right now. And we're also
Is that a collaboration as well with private industry at all, or is it solely by NASA?
This particular project, the technology came from a lab in Japan, Masateru Taniguchi's lab at Osaka University. There are many groups that have been studying what's called quantum electron tunneling, but the basic idea, it's a small gold wire, we bend it, we break it, we form an atomically sharp junction. And I alluded to its ability to detect single molecules and DNA, RNA bases in a very general way. That's because it's totally solid state. There's no biology involved. We're detecting the interaction of that chemical, that molecule or part of a molecule with that nano gap. And we can detect spikes in the current, and then we can use machine learning with different standards to understand how do the signals that we get relate to different molecular structures.
Wow, it's incredible. Cassie, how did looking back at the contamination that was done on Mars, how did that occur? I mean, it's not like an oil leak underneath.
So it's just the fact that the spacecraft have Earth compounds on them. Even the surface cleaning that NASA does is cleaning to the point of at least a limited number of living organisms. They're actually allowed to be living organisms even on the surface of spacecraft, but embedded in the spacecraft that can be popped off if the spacecraft break. A number of spacecraft that have crashed on Mars. The Earth organisms go wherever we send our hardware, and distinguishing between Earth contamination and Mars material is absolutely critical. I mean, every spacecraft we have sent to Mars has found indications of intelligent life on Mars, because every spacecraft we have sent to Mars has taken pictures of spacecraft. We just knew they were us. So distinguishing between Earth contamination and the thing we're actually looking for from the other planet is being able to understand what's the difference is absolutely critical.
The other question I want to ask, and I'm sure no one thought about this, well, maybe I did, but what happened to the earthworms? Your earthworm?
My nematodes?
Yeah.
We cultured them in the lab. I was actually in a coma at the time because I'd been in a bad car crash on the way to the airport, but my postdoc was able to retrieve them. We cultured them. We put them into the culture collection. They are actually called NCC for NASA C. Conley, but we wanted to have them be NCC in the Cinerabditis culture collection.
So they survived the crash.
They were just fine. Yes, we actually had a follow-on experiment, the International C. elegans first experiment that put worms back up on the space station and left them there for multiple generations. It's an ongoing research project that my postdoc is carrying out now in England.
You should write a book. Thank you. Yield back.
Congresswoman Brooks.
You talked, Dr. Connolly, about a committee in 2006 that had a lot of different participants. What happened to that committee? And is there a present day similar type of committee?
So I would say the present day version is probably the Space Studies Board subcommittee that was mentioned, but NASA, when I was got to headquarters in 2006, had a very robust advisory committee structure. They were the major NASA advisory committee had subcommittees, and those subcommittees had subcommittees that were operated as if they were FACA chartered. So everything was public, Federal Register published, everything was visible to the public. They were closed down as concerns within the NASA hierarchies started becoming more prevalent about people telling NASA to do things they didn't want to do, or more importantly, telling NASA not to do things they did want to do. And the Planetary Protection Advisory Committee, Bob was actually part of it for a while, was very strong in emphasizing that NASA needed to follow planetary protection effectively. And this is in the context of, in the design requirements for spaceflight missions, there is no requirement to be compliant with planetary protection sterilization modalities. So instruments being developed for Mars get no information, or at least are not required to provide any capability to tolerate sterilization until they're actually selected for a mission, which means they're already at TRL 7-8-ish. So within the NASA structure, there is not an appropriate support from the fundamental beginnings of the work for compliance, effective compliance with planetary protection. This actually goes back to the Ranger program, where the first 6 Ranger missions all failed. 5 of those first 6 missions in the 1950s failed because they were baked, but all 6 of them failed in a manner consistent with the small transistors they were using having foreign object debris that floated around in the hardware. And then as soon as you got into microgravity, it shorted things out and killed the spacecraft. To this day, people are still trained that the Ranger missions died because of planetary protection. So there's a major dichotomy.
What year did that committee end?
2006, it was changed. In 2009, it was canceled for a full year after they made some recommendations that were kind of objectionable to the NASA management structure. And then it was reconstituted in 2011 in a different format that did not have all of the federal agency representatives that it had previously.
And okay, thank you very much. Dr. Meyer, the treaty that you talk about that various countries participate or agree to, sign on to, or can you just explain the treaty process and how do we recognize either compliance or non-compliance with the treaty mandates?
So I think we've heard a fair amount about this today, and that this is the Space Act agreement that says we're going to explore Mars and explore space, and in particular, we're not going to compromise the science of planetary bodies that we're trying to understand. And so that's kind of the one-liner, for at least for science in their exploration of what they rely on, how to responsibly go forward, and we're not going to put Earth at risk in the exploration. And the way this is, let's say, put into effect is through COSPAR, which is the international space research body that basically they're the ones that codify what would be a reasonable approach to not contaminate bodies that you're exploring and not to contaminate Earth with stuff that you have been exploring in space and bringing back to Earth. So that's the framework of it. And spacefaring nations have signed up to this and they follow it.
How do we know?
It's not a law. What?
That's my question is, how do we know they follow it? That's my really crux of my question. How do we know that
at COSPAR meetings, there's a planetary, Cassie knows more about this than I do. Okay. At planetary protection, at COSPAR meetings, international meetings, there's a section on planetary protection, and nations report out, here was my mission, this is what I did. Here's how we complied with planetary protection and that sort of thing.
Is that after the fact or before the mission?
There's both. But
Well, thank you. You want to add to
Sure,
that?
it's self-reporting fundamentally. The US reported on Viking, the Russians reported on the Soviet landers that went to Mars. I happened to be involved as planetary protection officer in evaluating a Russian mission, the Phobos Grunt mission that was intended to collect samples and bring them back from Phobos. And when in the US, when Soviets said, oh yeah, we put our spacecraft into a nuclear reactor and irradiated them, everybody in the US laughed, sort of behind snicker. Oh yeah, sure you did that. In the I heard, because I speak Russian, in the back of the room when I was mentioning the Viking program, the two Russian scientists said, oh yeah, sure, of course they baked their spacecraft. Yeah. So it's self-reporting, and whether you believe it depends on.
So there's no independent body that verifies.
Correct. No independence.
Okay. No. Thank you.
Okay. Ms. Levinson, you have any questions?
Thank you.
Oh, I'm sorry. I'm sorry. I didn't see you there, Ken. Mr. Weinstein.
Blending in the background here. Just to put a fine point on it. And obviously there's no enforcement mechanism that comes along with that treaty to require a certain level of reporting from the nation state members, right?
No, the way that people enforce is by peer pressure. So NASA's requirements say that we will only work on missions that have COSPAR compliance.
And then there's nothing about the terms of that treaty that require the nation state signatories of that treaty to require some level of adherence to standards by non-governmental actors.
Yes, that's Article 6. Article 6 of the Outer Space Treaty, which has more than 100 signatory countries. Every country that explores space has signed the Outer Space Treaty. That Article 6 requires that states party to the treaty are responsible for the actions of non-governmental actors within that country.
Okay. But does it prescribe any way that the nation states are supposed to ensure adherence to those standards by commercial entities?
I don't think treaties do that. Usually it's in discussions. And so the UN Committee on the Peaceful Uses of Outer Space is where those things would be discussed. And they do actually have recently started a coordination with COSPAR in 2007, they recognized COSPAR as being the set of guidelines. And they have a the UN Committee on the Peaceful Uses of Outer Space is coordinating with COSPAR and ensuring, and COSPAR panel on planetary protection is where those things get reported. But again, there is no verification.
Right. So just trying to team this up with the conversation about lack of legislation.
Yeah.
That there's no legislation that prescribes a certain licensing mechanism for non-governmental actors. And there's nothing about the treaty obligations that actually prescribe some sort of licensing or other binding kind of process that governs commercial actors.
Correct. And the FAA only is responsible for things inside the Earth's atmosphere. That's important.
Well, that's interesting.
They don't regulate activities outside the atmosphere. That's why they couldn't, I don't know if they tried, impose penalties on Tesla for having the wrong trajectory after it left the Earth's atmosphere. But that was definitely one of the discussions that my advisory committee was having, was that there needs to be some way for the US to regulate activities outside the atmosphere as well as within the atmosphere. The FAA licenses launches and it licenses returns because they're coming through the atmosphere. Doesn't license anything else.
Is there something that says, I'm just curious, is something that says that their legislation stops with the atmosphere? Their jurisdiction stops with the atmosphere?
They definitely told me that when I was talking with them. And I don't remember what the constraint was.
Interesting.
Christopher Columbus.
Thank you.
Okay, Dr. George.
Thanks. So Christopher, recently we've been hearing about mirror life, mirror biology, and there are folks from Stanford and MIT and others who have called for a complete halt. Any type of research on mirror life should be stopped because of the potential negative effects on Earth life. Putting aside any judgment about whether that is the right thing to do or not, it seems to me that if we don't do any research on it at all, then if how are we going to find it or see it somewhere else? So how do you square that? Because I mean, it's a legitimate concern. They're concerned about something negative, occurring here. What do you think about that? How would you square it?
Well, I think I trust that my colleagues who were involved in that report, made some very good decisions when they wrote those words. So, I'm not an expert in the immune system. I understand that was one of the risks they highlighted was the inability to recognize the potential inability to recognize mirror image life and thereby prevent it from causing harm. That said, I don't think it's as simple as prohibiting all work on this topic. I think that would be a real mistake because anyone with a computer and the right machine learning model can do this kind of work now. And so I think it would be a very good idea for us to use at least our computational tools and understand to a certain point, what are the risks? Are they real? Are they not? What can we learn? Are there aspects that are useful? How would we detect it? Because I can only presume that there will be those who will choose to pursue this line of work, whether we have our head in the sand over it or not. And also, I do think that if we're talking about life beyond Earth, that's a real possibility. We don't know why life as we know it uses the handedness it does, and we may find that things are different elsewhere.
Agreed. Thank you.
So one more addition, if I may. I think it would be really important to distinguish what activities we think are safe and what are not safe, both from a standpoint of actually causing harm or producing products that could be misused or tools that could be misused. So I think those are areas where, as a community, the U.S. government needs to frame the discussion and ultimately develop guidelines like what research should be done, what shouldn't, similar to the discussions around gain of function research.
Which have gone so well. Michael, there have been questions about possibly not returning samples entirely to Earth, finding a different way to bring them back close, but not have them here for examinations. Some people have recommended the moon, but of course now you're contaminating the moon possibly, so we don't want to do that. Do we leave it out in space somewhere? Do we build a floating laboratory? Do we build our own planet somehow? What do you think?
So one of the major reasons for doing sample return is that then you can use the best instruments on Earth to do the research that you want and in methodologies that you're familiar with and can practice, et cetera. The problem of, let's say, having a floating laboratory, even if it's not in the Earth-Moon system, therefore not a threat to Earth, you have to deal with microgravity. You're going to have to deal with instruments that you have to design for the space environment. You're stuck with whatever instruments you pick to work with. It ends up, oh, why not just send the instruments to Mars and do your measurements there? Well, we've been trying that, and there's just things that we can't do still. And there's plenty of instruments that we can't put on a spacecraft going to Mars or in orbit around some other planet. Like synchrotron radiation, you're not going to fit something that's the size of a football field into your spacecraft so you can do some measurements away from Earth. So the major impediment there is that you end up with sort of the robotic model of how you look for life elsewhere, because then you're always stuck with last year's innovation at best and constrained by space, volume, and power.
Okay. And then Cassie, I'm sure you're aware of I don't remember which company it was, but somebody went up to the moon and decided they were going to drop off a bunch of tardigrades just to see, I guess, and see what would happen. And putting aside just the philosophical problem most of us have with just taking life forms and dumping them somewhere where there's no oxygen and there's nothing else for them. They're up there now. So one question would be, or possibly up there. I guess we don't know. We have to go find out what happened to them. So A, how would we find out what happened to them? And then the second question is this. You mentioned the problem, and Ken talked about it as well. The regulatory environment is such that the FAA has got this to this and this to this, and the Department of Transportation has something else, and Commerce has something else, and NASA's out because it doesn't have a regulatory authority, unless it's a NASA thing, so NASA can tell itself what to do, and NASA can tell its contractors to do, I guess, in theory. So we're hearing all kinds of stories now. People are just going up and doing nutty things, or things we think are nutty, dumping human remains, dumping tardigrades, doing whatever. So what do you think we need to do? Not so much what can we do given how things are, but what do you think we need to do?
I think there should be a committee like the Bat Contamination Committee that is based on following the guidelines in PDNSE 25, which were that you not only coordinate within the US when you have these potential experiments that are going to have wide scale consequences, but you also coordinate internationally. So the State Department was part of that. I had a State Department rep on my early committee. It's a global problem. There needs to be a global solution. When you're talking about sending things up to the moon, as I said, meteorites from the moon land on Earth, material ejected from Earth goes up to the moon. The worst contamination event on the moon was the Apollo program. They did not pack out what they packed in. So there are long-standing experiments in planetary protection sitting underneath each of those capsules, and it would be great to go up there and collect that material. I will note that we have, in fact, collected spacecraft sent to the moon and brought them back. The Surveyor 3 camera is the famous example, but the contamination that was reported as round-trip contamination on the Surveyor 3 camera, it was sent up robotically, retrieved by an Apollo mission, then sampled for organisms that were potentially surviving on this camera, on this piece of hardware. Then one of the astronauts heard that there was a cultured organism and got all excited about it. It's an organism that is commonly found in the human nose, and video recording that I funded to be analyzed when I started out as planetary protection officer in 2006 got documented that just before the sample was collected, a photographer had leaned in and taken a picture of the spacecraft, and then they sampled the spacecraft.
Okay.
Probably not a round-trip contamination event.
Right.
However, we have demonstrated in other experiments that were designed to show that Earth organisms can survive the near-Earth environment anyway, that it's possible. So when we have that much trouble differentiating between contamination and actual true result, that just shows that even when people are thinking about it, they screw up. And we need to really have much better oversight and guidelines and ensuring that things get considered from the very beginning of the mission development, spacecraft development, instrument development, program development. Commercial side definitely doesn't want to do anything that will make it more expensive, definitely doesn't, in general, modulo the regulatory confidence question, wants to have the minimum amount of effort required to do anything. That needs to be done in a coherent, preferably global, definitely federal level, coordinating all the different inputs from the different interest groups and not assuming that somebody's an expert and therefore they're going to do the right thing, because often the person who knows how to do it is going to cut corners.
Understood. And the tardigrades?
Tardigrades, I believe they were stuck between pieces of tape. And so my first question was, can they survive the solvent in the tape?
Got it. Okay. Christopher, did you raise your hand?
Yeah, I just wanted to add a one point here to advocate for using the moon as a test bed for planetary protection. And I think as a scientist, I really want to have the best science. As an engineer, I'm a little bit lazy. I don't want to do extra work. I want to have my hardware do it for me. So, or not have to do it. So what I think we could do, knowing that the moon and Mars are different environments, the transport mechanisms will be different, et cetera, there will be some commonalities. So maybe we do an A/B test. Maybe we explore what planetary protection mechanisms we might need to use on Mars, do it on the moon, and see what works, what might need to be applied differently. How can that information inform refinement, either making more or less stringent our planetary protection protocols. Thank you.
Okay, do any of the ex officio members have a question? Seeing none, we thank you very much, panel. The great presentations and great questioning. Thank you.
Yes, let me thank everybody for their presentations. They certainly have expanded our knowledge, but it also tells us about a lot of tensions. The private sector is not as interested in the research as they are getting people up there. They've also discovered a way to do this more cheaply, which means that anyone on Earth can build these rockets if they have the engineers or the models at least. But it also takes me back to our two recommendations, which are recommendations for the American government that may have to include some of the regulatory framework that we've talked about, as well as a little bit more international agreement about how the research is going to be conducted and protecting us against contamination, at least initially. But we've got to do all of this pretty quickly because everybody is going to be able to build a rocket. And not everybody, but certainly some countries that we don't like as well that may not be as responsible. And I think our two recommendations were fine for their times, but now they have to be expanded. And the purpose of today was really to find out what kind of framework, what kind of reconceptualization we need to do about this whole issue. And obviously our panelists have given us enormous contributions. I also want to thank you, Asha, for your excellent presentation on behalf of all the members of the commission. Thank you. Thank you, everybody.